And awesome. And move to the next slide. Okay, perfect. So today's agenda, I just lost myself. So today's agenda, we have 5 meeting topics. First, I'll go over, our welcome and introduction. I'll ask that people introduce themselves, and I'll walk us through that when we get there. And I will cover meeting logistics and how to participate. Before we dive in, I'll just read off the topics that we're covering today. So our first topic is data center energy efficiency opportunities, and Energy Trust of Oregon will be here with us today to help present that topic. And then price futures, we'll take a short break, and then we'll get into draft portfolio analysis results and the preferred portfolio, part 2. We'll take another break, and then we will go into our last 2 topics, which is our draft action plan, part 2, and our initiation for request for proposals, or RFPs. And now I'll go into introductions. So basically how this works, if you haven't been with us before, is that I will go down my list of participants as I see them on my side of the screen. And when I call your name, if you could introduce yourself and your organization if you belong to one. And if you are attending via phone, I'll use the last 4 digits of your phone number to call on you. Oh, just one sec. Okay, bye. Okay, so I can get started. My name is Jessica Graber. I work for PGE in our Integrated Resource Planning Department. And next up, I'll call on Alondra Regalado. If hopefully I said that okay.
You did. Hi, I'm Alondra. I work with the Western Energy Storage Task Force, and PG is one of the utilities that we cover.
Thank you. Amber Ryder.
Good morning, Amber Ryder. I work for PGE in the load forecasting team.
Thank you. Anna Kim.
Hi, I'm with the OPUC staff.
Thank you. Bill Henry.
Hi, Bill Henry, Pacific Ocean Energy Trust.
Thank you. Brian Mayfield.
Hey, Brian Mayfield with Clear Result New Buildings Program.
Thank you. Cindy, last name starts with S.
Hi, sorry, Cindy Strecker. I'm with Clear Result with Energy Trust New Buildings.
Thank you. Next, Dina Dubson Kelly.
Good morning, Dina Dubson Kelly with NovaGen Consulting.
Thank you. And Elaine Hart.
Hi there, Elaine Hart. I'm an independent consultant supporting the Oregon Public Utility Commission.
Thank you. Jake Wise.
Jake Wise, PGE liaison to the Energy Trust.
Thank you. Jason Solmy-Klotz.
Oh, good morning. Jason Solmy-Klotz. I'm with Portland General Electric. I'm in our planning department.
Thank you. Next up, I have Jeffrey Barrett.
Hi, Jeffrey Barrett with Apex Clean Energy. We're a renewable energy IPP.
Thank you. Next, I have Joe Boyles.
Hi, Joe Boyles, Portland General Electric.
Thank you. Okay, next, John Robbins.
Good morning, John Robbins with Mitsubishi Power.
Welcome. Next, I have John Bickerton.
John Bickerton with New Sun Energy.
Thank you. And Kim Herb.
Kim Herb with the Oregon PUC.
Thank you. Michael Swanson.
Hi, Michael Swanson with Clear Result and Energy Trust New Buildings.
Great. I have an attendee with the first name Nick without a last name listed, if that might be you. go ahead. I also have a Nick Henriksen as the next person on the list.
Hey, this is Nick Henriksen. I don't know if I'm both Nicks because I'm on my phone as well. So, but Nick Henriksen with Pivot Gen, we're a wind and solar developer.
Thank you. Next up, Nahit Shah.
Hey, good morning, everyone. My name is Nahit Shah. I'm an analyst on the IRP team, PGE.
Thank you. Next is Pat Shaughnessy.
Good morning, I'm Pat Shaughnessy. I'm an analyst with the Oregon Public Utility Commission.
Thank you. Next up is Rainbow Wong.
Morning, everyone. I'm Rainbow Wong. I am an analyst on the IRP team at PGE.
Perfect. And I've got Randy Hardy next. I know sometimes Randy calls in from his phone. You might have to press *6 to unmute yourself if you're on your phone, Randy. And we can always come back. Okay, let's go to Rob Campbell.
Good morning, I'm Rob Campbell. I'm an analyst on PGE's IRP team.
Thank you. Next, Sashwat Roy.
Hi everyone, Sashwat Roy with Renewable Northwest.
Thank you. Seth Wiggins.
Good morning, everyone. Seth Wiggins. I manage the Integrated Resource Planning team at PGE.
Thank you. Shelley Carlton.
Good morning, everyone. I manage the New Buildings Program for Energy Trust of Oregon.
Welcome. Thank you. Next, I have Stephen Brown.
Good morning, Stephen Brown, PG Regulatory Strategy.
Thank you. Sudesh Nepal.
Good morning, this is Sudesh Nepal with Oregon Public Utility Commission.
Thank you. Next up, I have Tasha Bryan.
Hi, I'm Tasha Bryan from Bonneville Power Administration's Long-Term Commercial Planning.
Thank you. Timothy Powers.
Yeah, hello, Timothy Powers with Innovative Solar. We're a solar developer.
Thank you. Trisha Paul.
Hi there. Sorry, it took me a second to unmute. Trisha Paul with Clear Result, energy efficiency consultant.
Thank you. Okay, I know Randy is here, but I couldn't hear him before. Randy, are you available to introduce yourself?
Yeah, I'm here.
Okay. And do you want to introduce your organization?
Randy Hardy, Hardy Energy Consulting. I do consulting for a variety of wind and solar developers.
Thank you. Okay, that is everyone I see on my list. Did I miss everyone, or did I miss anyone as I went through that?
Hi, it's Fred Hewitt, Northwest Energy Coalition. Good morning, everybody.
Morning, Fred. Okay, well, thank you all for being here this morning. Let's go on to the next slide. I'll do the meeting logistics. So an electronic version of this presentation is going to be on our website tomorrow after the meeting. We have our meeting information, Zoom details listed here. And for participation today, we'll be taking verbal questions. So we're going to ask that you use the raise hand feature, or if you're on your phone, to unmute using *6. I'll review more facilitation details on the next slide if you can move on. Thank you. So today we're similar to our previous meeting. We are taking clarifying questions during the presentations. So as the presenters are providing information, go ahead and raise your hand. I'll be able to see who has their hand raised, and presenters will take questions as they move along. You won't have access to the chat during the meetings. We're trying to streamline our ability to give and take feedback so that we can pay attention to one venue. So if you do want to type out a longer question or comment, we do have multiple ways to do that. You can submit a form that's on our website. It's a public feedback form, or you can email us at irp.pgn.com. If there are, so we have clarifying questions during the presentation, and then after every presentation, there will be time to take questions at the end as well. So if there's a question that seems a little bit longer, or we want to get through the last slide and then answer the question so you have a full picture, we might ask you to hold a question or to keep the meeting on time and on topic. So if we do that, I'll probably interrupt you, and then I'll let you know that we can take that during the question and answer. There might be a case where a question is off topic for this meeting and we don't plan to address a certain topic. And in that case, we can follow up with you after the meeting. Any questions here before we move on? Okay. Go ahead and move to the next slide. Great. So this is our first topic for today, data center energy efficiency opportunities. Seth Wiggins will introduce this topic, and then we have Andy Iden with PGE and a couple people with Energy Trust of Oregon with us today to present. So Seth, when you're ready, you can go ahead.
Thanks, Jesse. So good morning, everyone. I am Seth Wiggins. I'm not Andy Iden. Andy can't join us today. Unfortunately, he's out sick. So the combination of myself and Amber Ryder are going to cover the first part of this presentation and then move to the ETO. To that end, we might be less than 100% effective in answering questions on the first part of this presentation, but we'll do our best, and hopefully Andy is right as rain in the next day or two, and we can get back to any questions on that. So with that, Shadi, if you could move please to the next slide, just to give some background on this presentation. So as part of the last IRP, the 2019 IRP, there was some discussion, I know in the docket, maybe even before we filed, around the load forecast with the industrial sector. So there was strong growth projected back in the 2019 IRP, as well as in this IRP in the industrial sector. And a large part of that was focused around, this tech sector, these data centers. And so in the 2019 IRP docket, I know we were discussing a bit about, that forecast, how appropriate it is given the opportunity for energy efficiency to come in and take a chunk out of that growth. Those data centers, the thinking went, if they could be more efficient, then we would see less load growth. That would lead to lower levels of resource need. And so there was a lot of discussion there. The result of that discussion was the commission weighing in and saying that it would be appropriate in this development of the next IRP, which is this IRP, the 2023 IRP, a discussion surrounding the energy efficiency opportunities at those data centers. And so towards that end, we are having this presentation to bring in the experts to think about that and to see what opportunities there are. We've been working, as we've discussed a couple times in the IRP roundtables, we have close coordination with the ETO for the forecasts of both cost-effective and non-cost-effective energy efficiency. And we've discussed a couple times how that data is going into our models and what the results are. That will be the same today. When we get into portfolio analysis, we'll talk about the implications of that non-cost effective energy efficiency as well as the cost effective. But they are here today also to discuss these opportunities at our at the data center growth that we're projecting. Hopefully this makes sense. If you could go to the next slide, I'm going to turn presentation over to Amber Ryder, and she'll cover the next few.
Thank you, Seth. Good morning, everybody. So I'm just going to cover a little bit about the data center market in the region, and then pass it off to Energy Trust for more technical information. But so here we're just going to start with kind of what is a data center, what are the types of data centers. So, you know, a data center is physical space that centralizes that equipment for storing and processing data. And so as it says here, it can be as small as a closet, it can be as large as an entire building or huge span of buildings. So there's a few different types. One is on-premise. And so when you think of something as small as a closet, it's probably a on-premise data center located on site at a specific company to support that company's data center, their computing and data processing needs. Another would be co-location. So co-location facilities, we started seeing, you know, in Oregon a few years back. And those are large facilities. They offer data center services to multiple clients. So they're leasing space in one large building for different clients, but in that same facility. And then what we've seen recently in the market is the onset of mostly hyperscale facilities. So these are really large facilities. They might be owned and operated by a company it supports, or they might be owned and operated by a co-location provider, but have one large hyperscale client as a tenant. So this building would be, you know, primarily suited to meet that customer's specific needs. This is what we're seeing with a lot of large social media and technology companies. We can go ahead and move to the next slide. This is why our data center is coming to Hillsborough. So there's great access to trans-Pacific cables. And then we kind of walk through clean and renewable power options. So some of PGE's recent large customer programs over the last few years, and also the availability of hydro, favorable weather. Data centers need to stay cool. So we have a milder climate than a lot of other regions in the US. Cost of living and education. This is always, I like to think of these as comparable. We have this great, between the Bay Area and Seattle, Portland's a little bit cheaper. We still have a really educated workforce. And then data center clustering is all happening out there in Hillsborough. There's benefits to having the fiber ring out in Hillsborough, and latency benefits in being near each other. All right, let's go to the next one. So this slide just comes from CBRE Research, which is a commercial real estate research insight. And so what this is looking at is the Hillsborough data center market inventory and under construction. So you can see that these reports have really highlighted the growth in the Hillsborough data center market in recent years. That inventory has increased quite a bit, and construction implies that, you know, the increase will continue. This report shows, or these sets of reports, these are released semi-annually. They're pretty interesting, but Hillsborough is one of the primary secondary markets. So they've split these into primary markets. Primary markets have, you know, much larger market than Hillsborough itself, but Hillsborough has really emerged as one of the newer secondary markets that's growing quite rapidly. All right, and then so the next slide looks at just PGE's energy deliveries. So we've experienced rapid growth in industrial deliveries in recent years, and high-tech manufacturing remains the largest segment, but data centers are really emerging. And you can kind of see that in the visual over on the right. So the green is what data centers look like. So growing rapidly, but still that high-tech bucket is much larger. And I just wanted to point out here, I made a little notation that while traditional NAICS sector coding often calls data centers commercial customers, when PG is reporting, we're usually talking about voltage level for how we classify customers. So those customers, those large data centers receiving service on primary service voltage are going to be included in our industrial energy deliveries. And so then on the lower right, that's kind of showing you what the industrial energy deliveries growth has been over the last 5 years. As you can see, very rapid with, again, data centers as an emerging segment within the C&I deliveries. I guess I want to just use it appropriate to pause for questions now before we pass it off to ETO.
Yeah, I think so.
All right. So if anybody has any questions, otherwise, yes, that will be the time to pass it off to, I believe, Spencer presenting for ETO.
And Amber, if you see people's hands, you can go ahead and call on them.
Okay. I see Elizabeth.
I read in the Oregonian that some of the data centers are providing their own power, and so they don't have to follow the 100% clean energy. Do you have any comment on that?
I don't have any comment on that. If anyone else wants to jump in, I just am not informed on that one. Okay, we can follow up with you.
Yeah, I'll note it down and I can ask Andy if there's any follow-up. Thanks.
Thank you. Okay,
other questions? Okay. That's if you can go to the next slide, Shadia. So I think we will hand over to Energy Trust, and I think it's Spencer who is with us today. Spencer, when you're ready, you can go ahead and just let us know when you're ready to move to each next slide.
All right, great. Thanks a lot, Jesse. Good morning, ladies and gentlemen. My name is Spencer Morsfelder. I'm the planning manager at Energy Trust of Oregon. And consistent with what was said earlier, PGE reached out to us to provide some information and perspective that resulted in a two-part presentation, which is what we're about to walk with you through this morning. The first part is about how Energy Trust forecasts energy efficiency potential and how that relates to the energy efficiency potential associated with data centers. And the second part is perspective on what Energy Trust New Buildings program is offering and doing to serve data centers. The emphasis on the New Buildings program is primarily because the question is focused on how is Energy Trust providing offerings and opportunities for data centers, new data centers, to save energy. Next slide, please. So Energy Trust does work with PGE to provide an energy efficiency forecast consistent with PGE's integrated resource planning process and cycle. And we provide a forecast of cost-effective achievable potential to help PGE understand how that resource fits in the midst of the options that they have to meet their customer needs through the IRP. So the forecast provides an estimate of the 20-year energy efficiency potential and the associated load production, and it helps with the IRP process. It also supports Energy Trust forecast of future savings and helps to provide a foundation for Energy Trust to work with PGE to put together an annual budget and revenue need to fund Energy Trust programs in order to reach customers. Next slide, please.
Hey, Spencer, can I interrupt you for 1 second?
Sure.
I have an administrative item.
Go ahead.
So I'm getting a notice that the Zoom meeting is, it's gonna like automatically end in 6 minutes. And so I think what we're gonna do is it'll end, Shadia is gonna fix it, and then you can rejoin via the same link. Shadia, is that right?
Okay, so let me stop sharing and let's take like a 2-second and I might be able to fix it. Something happened with Zoom. Apologize to everyone.
Okay. So hang tight for just like 60 seconds. Apologies, Spencer. And we'll see if we can fix this and move forward. Okay, I saw a notice that the meeting's been extended to unlimited amounts of time, which is both scary and glad that and happy that we could fix it. So Shadia will start sharing those slides again as soon as she can. Thank you, Shadia, for fixing that.
Right, so I guess it's back to me.
Yes.
Great, thank you. And thanks for remedying that before everything just disappeared. That would have been a little shocking. This next slide is a busy slide. I included it in order to help folks see how the forecasting process is working at a high level. And I'm going to walk you through that without going into too much detail. This is a flow chart, and essentially what it does is take measure level information and scale that based on the inputs that we're getting from PGE. We use that information to model the technical energy efficiency potential. And for those of you that are familiar with the power planning process, we convert technical potential to achievable potential based on the same multipliers that the Power Council is using for that conversion. The same multipliers that the Power Council used for the 2021 power plan. And the idea here is that technical potential is all of the places where an energy efficiency measure could technically be applied, but it isn't anticipated that it's going to be possible to install energy efficiency measures in all those applications. So there is a duration to convert technical to achievable potential. The next step that Energy Trust uses is a cost effectiveness screen based on a total resource cost test. And essentially what we're doing is checking to ensure that the measures that are coming out of the modeling process are cost effective based on the most recent set of avoided costs to represent the most recent set of economic circumstances that PGE is seeing in the market. And then finally, we take that cost-effective energy efficiency potential and deploy it. And that deployment is a representation of what Energy Trust actually expects will show up in the market over the 20-year forecast horizon. So that cost-effective potential is reduced to represent that 20-year deployment curve. And the principles that we follow for that deployment process, again, reflect some of the principles used by the Power Council, namely for discretionary energy efficiency measures or retrofit measures, if you will. We're assuming that about 100% of that savings potential will be achieved over the 20-year forecast horizon. And for lost opportunity measures like equipment that fails or new construction, we're saying that over the course of the forecast horizon, the penetration of the efficiency measures for those two types that I just mentioned, the failed equipment or the new construction, is going to increase as Energy Trust has more influence on the market and as codes and standards go into effect. It isn't necessarily clear in the out years of the forecast horizon what portion of that savings is going to come from Energy Trust programs versus market transformation resulting in codes and standards. I think one thing that's important to say is that forecast that we provide, that final deployed savings forecast that we provide, accounts for conversations that Energy Trust Planning Department that works on the efficiency forecast is having with Energy Trust programs to talk about what programs think they can achieve. And those achievements are based on current market conditions, understanding of the policy environment and the related revenue that Energy Trust will be getting from PGE in order to serve ratepayers to bring the savings potential through the door. So that was a pretty abbreviated version of this slide, but did wanted to provide that perspective for folks that aren't aware. I'm going to advance to the next slide, and then maybe before we transition into the new buildings program portion, if anybody has questions about this that we can handle quickly, I'll try to do that. So the question at hand for today is, how did data centers show up in the energy efficiency forecast? So the way that we're accounting for this is essentially we are taking the load forecast that we get from Amber's team, and that is a load forecast that needs to be converted to square footage because our measures are scaled based on saturation assumptions on a square footage basis. So we take that load forecast and convert it to square footage based on EUI information. The model that we ran most recently is based on an assumption that the EUI for data centers is about 542 kilowatt hours per square foot. And what we end up doing then is getting that square footage. We back out the square footage using the load forecast from Amber's team to come up with a total square footage for data centers in the industrial sector at large. And then we scale that for the prescriptive measures that we have and for our understanding of the custom savings that we'll be seeing for data centers. The number of prescriptive measures for data centers is relatively limited at this point. We have some shell measures that are currently in the model. We also have like a server closet mini split air conditioning measure, but that's a relatively limited measure in terms of scope and savings potential. The custom measure potential that shows up in the model is largely based on us going back, taking a retroactive look of the custom savings that have come through from historical commercial and industrial custom projects, and then applying that to the future based on that square footage assumption. And in the process of having this conversation with PGE to set up for this presentation, we recognize that there are some improvements that we can make to refine the methodology that we're using to forecast in the future, namely just making sure that the load forecast associated with data centers is refined for the future. But those improvements, I don't think, are going to have a dramatic influence on the amount of cost-effective achievable potential that deployed forecast that we give over the 20-year horizon. Moreover, that 5-year forecast that I was talking about before is more specifically tuned via those conversations that I'd mentioned previously that Energy Trust Planning that works on the efficiency forecast is having with programs. So I'm going to pause here because I think the next slide leads into the presentation that the new buildings program is going to be giving, and see if anybody has any questions about what I just described for the efficiency forecast. Jesse, I can't see comments, so I don't know if you're seeing anything there.
Yeah, I'm not seeing anybody yet. Oh, Fred Hewitt just raised his hand.
Hey, morning, Fred.
Hi there, Fred Hewitt, Northwest Energy Coalition. So I'm wondering, you mentioned the EOI, that energy use index approach here. For
Yep.
data centers. Sorry, go ahead.
I was just confirming that what you said is, I'm sorry, go on.
Yeah, so just to ask if for data centers specifically, especially because it's a very high energy density per square foot or whatever measure, is that do you adjust that based on, I don't know if there are any trends in the data center world, for tier one or, large data centers for increased energy density per square foot, as time goes on, or decreased if there's more efficient use, I guess. I'm just wondering if that's a moving target, because it seems like a pretty central part of the process.
Yeah, you're right, Fred. And yes, we do make periodic adjustments to the model, including our assumptions associated with this EUI to scale to the square footage. Just out of curiosity, I did a information search in the midst of developing the presentation, and I think that 542 kilowatt hours per square foot is still ballpark with what's happening in the market, but we do have an eye on this, and we'll be making updates periodically to the model, and certainly for the next modeling process for PGE.
Okay, thanks.
Yeah, thanks for the question. Jesse, I don't see any other hands. Have any other comments popped up?
No, I don't see anybody. We can always take more questions about this during the question and answer session at the end, if you'd like to move on.
Okay, great. Well, at this point, if I'm not mistaken, this is the portion of the presentation that gets turned over to the new buildings program team. So I'm going to have them step in and deliver from here on out.
Thanks, Spencer. Good morning. I'm Cindy Strecker, Engineering Director at Clear Result. We are the program management contractor for the new buildings program. I personally have been supporting the program since 2010, and some of my earliest projects that I worked on were data center projects. So I just want to give a little bit of a historical look at how we've worked with these projects. We have been supporting data center projects since 2009. For the first several projects that we worked with, we actually were developing custom baselines and supporting each of those projects individually while we really dug in and researched the data center market. So some of that early work included some market studies, a baseline study that Energy Trust contracted out with GluMac. There was also baseline documents that have been developed over the years by some of the other utilities, particularly down in California. So we really looked a lot at these different data sources to try and understand, what is a baseline for a data center project. Following those early projects, we actually created a program-specific Energy Trust specific baseline document, clearly defined the system types and equipment efficiencies that would be used by each data center project that was enrolled in our program. So depending on the size and type of data center, that would sort of dictate what their baseline systems would be. As we gained experience working with those projects, we did develop several calculator tools that could be used. Those early offerings focus not just on the mechanical cooling and the electrical distribution systems, but also on the ITE itself. One example of that is one of the calculators that we developed was for server efficiency improvements. In 2019, we had an evaluation of one of our data center projects that actually led to Energy Trust again hiring a third party to review our data center baselines. And in that review, it was actually recommended that we move to using ASHRAE standard 90.4. So that was a new standard released in 2016 that was specifically for efficiency in data centers. So if you go to the next slide. Oh, actually, it looks like maybe one was not included. So let me go ahead and just talk a little bit about what we're doing now. Because of that report that was done and that recommendation that came out, as well as the fact that Oregon had moved to having an energy code that was based on ASHRAE standard 90.1, which was the commercial energy efficiency standard, we actually began crafting an offering that was based on 90.4. That was actually further supported by the fact that in 2021, the Oregon Energy Code actually incorporated 90.4 as part of the Energy Code baseline or standard. And just a side note that these ASHRAE standards, they're on a continuous maintenance cycle where they're updated every 3 years. So the offering that we developed was actually developed using the 2019 version and not that 2016 version of 90.4. So we tried to use the most current one. The standard requires that the data center design meet minimum performance levels at 4 different loading levels, so 25, 50, 75, and 100%. Basically ensuring that the data center is going to operate efficiently over a wide range of potential loads. But what it doesn't do is it doesn't give us a direct pathway to actually identifying annual energy savings for doing better than this minimum performance level. So we created a tool that uses that minimum performance requirement, the design performance of the design data center, and then the actual expected loading that data center is going to see over the first 2 years of operation to estimate the annual savings. So the last thing to sort of note about this is that our offering really does only apply to the mechanical and electrical distribution system, and we don't address the server efficiency or any other means of sort of load reduction. So if we go to the next slide, okay, so these are jumping around. This chart shows the program savings over the last few years with the total number of projects shown against the axis on the right there. We did see a bit of a slowdown in projects that were enrolling in the program, and that's reflected in the low number of projects that are closed in those first 3 years there. We are seeing that number increase. It's also maybe just worth noting that historically we've closed somewhere around 30 different data center projects. And the peak was actually back in the mid 2010s. But on average, we've had about just under 3 projects close each year since 2011. And with this new data center offering that we have, that was just released last year, we are starting to see a bit of an uptick in project enrollments. So let's see what the next slide is. Oh, we're all out of order. Okay. I talked about this one, so we can go ahead and jump to the next one. And this one actually is just going to give some information about the projects that we've got enrolled in our current offering and sort of the savings levels that we're seeing. So on average, our savings are about 400,000 kWh per megawatt of ITE load. But you can see from this table that range of potential savings is actually fairly significant, and that doesn't, it's regardless of what the size of that data center is. Not all of these projects have closed, so the savings in the end could vary. And the reason for that is that the loading really drives the savings. We're looking at only the first 2 years of operation in the program. And what we've seen over the last 10 plus years is that some of the data centers will load up very quickly. So very high loads, obviously you're going to have higher savings. And other projects may take many years to actually reach their expected design loadings. So that does have a pretty significant impact on those savings that we claim. Let's see, next slide. So what kind of participation are we seeing? I did say we're seeing a little bit of an uptick lately in project enrollments with our new offering. We do see some of the same data center customers in the program. Sometimes they're building their own data centers and sometimes they're actually tenants in others. So we do see some changes in the planning of what they're going to actually include in their data center designs. But conditions sometimes are changing and making that a little bit more challenging to understand and follow. Artificial intelligence and some other technology changings are actually causing some hyperscalers to reconsider liquid cooling architecture to serve those higher compute loads. Other projects have actually hit pause in their construction so that they can reconfigure. In fact, one campus was actually stated to be liquid cooling ready in the event that their tenant decided to flip their cooling strategies. We've also, supply chain issues is not new news, but it is something that also affects data centers. And so, obviously being able to get the materials that are needed, both to create the physical shell as well as the wiring and internal structure. So a lot of that has gone up in price, and some of it has had limited availability, and that's really been driving some of the schedules and make it challenging for some of these projects to hit their deadlines. Like I said, we're gaining traction with this new offering, but privacy concerns are always going to be there, despite all of the steps that we take to address that. In fact, we've even seen some of the mechanical design team not wanting to share calculations that their tools that they've created to show the 90.4 calculations and how their data center designs are going to perform against 90.4. So it's just something that we're always going to have to address is the privacy issue. Next slide. Okay, so that was it. If there's any questions, I'm happy to answer. We also have some others on the team here that can help to answer questions about the offering and participation.
Thank you, Cindy. So if you have questions for Spencer, Cindy, or any of their colleagues, we can go ahead and raise hands. Okay. Anyone want to return to any of the slides while we have a chance to do that? I can take a look at those if you're interested in that as well. Okay. So I'm going to move us on to our next topic. I want to thank Spencer, Cindy, and the rest of their team for being here and for putting together all this information for us. This material will be on our PGE public meetings website. We'll post that tomorrow. And so if you have follow-up questions for any of the people who presented today, definitely reach out to us and we can connect with them and get you answers for questions that you have. So thank you, Spencer, Cindy, and team. Okay, the next topic is price futures. Rainbow Wong will be presenting, and I think Seth, you're gonna take the introduction for this topic. Is that right?
No, sorry, I meant for the portfolio analysis.
Oh, okay, great. So Rainbow, whenever you're ready, you can go ahead.
Great, thanks, Jesse. Hi, everyone. Again, I am the IRP analyst on PGE's team, and today I'll be giving you an update on price futures. Shadi, if you can advance to the next slide, please. So our update today is going to be focused on the evolution of price future creation, and specifically, we're going to talk more about the PGE's carbon policy assumptions that is currently in the price future creation that is then used for portfolio analysis. And the chart below is sort of busy, but really this is to give a high-level reminder and update on the evolution of price future creation. Across the left side of, up and down on the left side of this table is all of the components of risk that we incorporate in our price future creation. And as you see here, I've highlighted the carbon policy that is part of the price future creation, and across the page are the updates that we have brought to this group during various times of roundtables whenever we have an update or a sort of change in methodology. So I won't go into the detail of all of the risk components that's part of price future creation, but today I'll be focused on the carbon policy that our assumptions have changed over time. So back in April of 2022, we've applied a carbon adder to carbon emitting resources located in California, Oregon, and Washington for the reference price features. We also applied the carbon adders to only California carbon emitting resources in the low price futures. And we apply a social cost to all of the high carbon price futures for California and Washington. Then in November, we decided that we were going to create some no carbon adder price futures to really kind of see the difference of the counterfactuals. You know, what happens when, you know, how do emitting resources behave when there are no carbon adders added. But then we realized that, you know, that's in the world today where we're really focused on clean energy, that may not be the most plausible scenario. And so we kind of went back to the drawing board and finalized our carbon policy assumptions in February. And so the final set of price futures that we have today is where we apply a carbon adder to the carbon emitting resources in California and Washington only, because and in the reference case, and this is because there are existing carbon tax legislation in both of these states. We then also remove the carbon adders to carbon emitting resources in Oregon and the rest of WEC in the low carbon case to again reflect what is actually happening today. Ultimately, we created 39 price futures that are then used in our portfolio analysis. And Shadi, if you advance to the next slide. This slide is to highlight the impact of carbon policy changes to the Pacific Northwest electricity prices. On the left side, this is a chart of the carbon adders that we're talking about that's going into the price future creations. And then the two following graphs on the right is to show you the impact of what happens when the carbon policy is changed. Previously, we had a carbon adder to California, Washington, Oregon, as well as a slightly lower carbon adder case to the rest of WEC, and also a tax adder to British Columbia and Alberta, which stayed the same over time with the different evolution of carbon policy assumptions. And as you can see now with the new reference case where we don't have a carbon adder for Oregon and WEC, the electricity prices by definition is lower because there are less carbon adders. Again, because of the carbon policy assumption change we made also in the low carbon case, on the right side, you also see that the current electricity prices for a low carbon case is lower than what it was previously. And then on the bottom of the page is really a reminder of the codes that we're using, RRRR, what that stands for. It stands for our reference case where we're referencing the WEC build out outlook. And we have a reference case carbon adder and a reference case gas price forecast, as well as a reference case and in a hydropower generation condition. And so I'm seeing some hands up, so maybe I could start answering questions.
Yeah. Are you finished with this slide? Okay.
Yes.
Yeah, go for it.
Yeah. Yeah. Thanks, Jesse. Elizabeth.
I wanted to find out what a carbon adder is. And I wanted to understand if your numbers between 31 and 42 are higher or lower, what that means.
Okay, sure. Maybe Shadi, if you can go back to the previous page so everyone is oriented with what Elizabeth is talking about. So a carbon adder is something that we added into our price simulation to because the price simulation is has a simple logic of an economic dispatch. So, you know, the simulation really compares the price of running a thermal plant. And so when there's a carbon adder, meaning that there's a higher price to run, to turn on a resource, how is that going to affect the amount of time and when this resource is getting used to be dispatched? And so if you can kind of think about—
Are you saying that a carbon adder means that the state might use thermal or methane electricity generation?
It's more of like an—
I can jump in here.
Okay.
It's a good question. So we in IRP, we're creating this economic plan, and we're supposed to focus on cost and risk, quantifiable. And so when we talk about carbon prices, we have to focus on what's been called the cost of carbon compliance. So basically, when we think of all the costs and benefits of the market, we have to incorporate the costs that we expect to be paying. Now, when we say carbon adder, what we're saying is it's basically a modeling term where we are incorporating the that cost of carbon compliance, basically saying like, well, if there were the easiest corollary is if there was a carbon tax, say in Wyoming, this is hypothetical, we would say, okay, in Wyoming, we are going to put a carbon adder into our production cost model, Aurora, that simulates basically the economic decision that those plants would be making with that carbon tax. So the way Aurora works is kind of weird, and so we have to implement these carbon adders through a transmission component. It's not really worth getting into the details as to how we do it, but basically we're trying to simulate that carbon tax or cost of a carbon policy. Washington and California have those, and so we're trying to simulate the effect of those in the market price simulations.
Does Oregon's 100% clean energy bill have the effect of being like a carbon tax, or it doesn't operate that way?
Yeah, that's a great question. So the answer is no. HB 2021 has limit on emissions, but not on a cost associated with the dispatch of thermals. And so, you know, effectively, they're aimed at doing the same thing, reducing emissions, but they're doing something a little differently. And the reason why we're making the change now to say that Oregon doesn't have this cost of carbon in it, because the regulation is focused on our emissions. That's incorporated into our plan. That's, you know, representative of all the portfolio analysis that we're doing, but we're not going to be facing this cost of carbon compliance in the dispatch decisions, which is why we're taking it up.
And does the 31 to 42, does that reflect what might be a carbon tax kind of substitute?
So are you referring to the total price futures on the bottom?
Yes.
Okay, so that's just the number of price futures that we're incorporating into our models. It was 31, we increased it by a couple, and now we've decreased it down to 39. So we're going to—
So you mean the number of scenarios?
Yes. Yeah.
Okay, thank you.
Yep.
Seth. Elaine, I also see your hand up.
Thanks, Rainbow. If you could go back to the slide 23. I guess my question is about the implications of this, maybe and other changes since prior roundtable meetings. So my understanding is you've got Colstrip continuing in the portfolio through 2029, and I'm curious what type of dispatch behavior you see from Colstrip and if it's changed as a result of these changes to the carbon price approach?
Sure. So it so previously, coal strips retirement was in 2025, and we've extended it to 2029, given in the negotiation and sort of the strategic planning behind filling capacity. And so generation has increased because of this change, as well as the lower electricity prices in the new carbon policy assumption changes. But PZM as a simulation is not, or in Aurora is not the best, I'd say, representative of retail generation, because that's now taken care of by the GHG model. So we have seen a slight increase in total generation with the new carbon policy change between 2025 to 2029 because of this retirement extension. But Aurora as the model does not really bifurcate the generation that is associated with wholesale or total generation versus retail.
Yeah, I think that's right. And if I could just add to that. So it's important to note that our total emissions associated with serving retail load are still hitting the same trajectories, whether it be like the reference linear decline or the others that we've evaluated in portfolio analysis. In general, this change is a pretty simple one. So as you lower market prices, that increases the economic dispatch of existing thermal units. The bifurcation between serving retail load and for wholesale sales is affected such that the increased generation of all of your plants are going, basically, if you maintain the same emission decarbonization glide path, then the increase in emissions is shown in wholesale sales, and that's reflected in the economics of basically all the portfolio analysis that you'll see in a couple slides.
Maybe I need to make my question a little bit more specific. So in the past, there was, my understanding was a carbon price applied to coal strip. And so you would often see it dispatching at kind of its min level on a forecasted basis because of the penalty of the carbon price. And my question is just specifically if you're still seeing that, or if it economically dispatches at what you would expect, maybe higher levels that are not affected by the carbon price due to this change. And maybe if you could clarify what you mean by you see the, I'm not sure I can exactly remember the phrase that you said, but can you explain the differentiation here between wholesale and retail? Are you saying that these things are running, but you're selling it into the market, so you're not counting the carbon?
That's well, to be clear, we count all the emissions and all of that is displayed in portfolio analysis. Okay. So regardless of the plant was running 100% capacity factor in all of our plants, we would still count for that and present that information.
Got it.
So in general, you're seeing it's a pretty straightforward economic effect. The lower price leads to higher dispatch. The exact dispatch of coal strip between, it's P-min versus the minimum level of production that it has to have given, all operational characteristics of the plant and contractual characteristics of the plant versus a, more economic dispatch. I'm not sure. We didn't look at that specifically, but we can take a look and try to get the answer for that. But in general, coal strip and all other plants see a higher economic dispatch from this change.
And I would expect that not to be because the prices are lower, but because they're not being penalized with the carbon price, because lower prices will tend to reduce your thermal dispatch. But I can save that follow-up question for another day. Thanks.
Thanks, Elaine and Seth. Fred, I also see your hand up.
Yeah, on a different topic on the gas price forecast. It wouldn't be a PG IRP meeting or any IRP meeting for me if I didn't talk about gas, right? So anyway, as we have seen over the last several months, there have been a rather dramatic change in the gas prices in the region, and therefore also the market price, the power market prices. And I'm not real. I mean, I think that's the part of the question I really have is that changing your views actually on the use of the gas forecast? And I'm actually not so much talking about that period in November, December, January, where gas prices were, normally in the single digit range, we're in anywhere from $20 to $50 a million BTU. But rather the situation we're in today, which is that gap between the kind of national price, mostly represented, most people would refer to the Henry Hub price. Henry's in Louisiana. It's kind of a national standard pricing hub for natural gas. We have now entered a phase where I think we have, instead of differentials, the traditional term was, you had a Henry Hub price, and then you had a price for another pricing hub. For example, Sumas, the one that is in the Canadian border, in the gas pipeline that goes to the Northwest from British Columbia, that the differential, I talked in terms of differential with Henry Hub, usually would be, some few cents or some, relatively low percentage. So, a 10 or 20% price differential. That is out the window now. Henry Hub is $2.50 this morning, and the price at Sumas is $8.20, and it's higher in California. So we see a new kind of separation between the national gas market and the West Coast gas prices. And I'm wondering, this could diminish over the next few months, but it seems to me we have to now consider a new situation where the national price forecast, like you're getting from WoodMac or other suppliers, will have to, they're going to have to, if this kind of thing continues, they're going to have to revise their forecasts and start looking at regional price separation like this as a distinct possibility. I mean, it's very hard to predict. So I'm just wondering, I'm sorry to give this big, long run up, but this is a really important driver for the pricing forecast, is what happens with gas prices, and specifically what happens with the gas prices for the gas that power plants and utilities in the West and in the Northwest, and PG, of course, specifically, are having to pay. And, realizing that all this is happening at the very end of the IRP process, I'm not asking for any major changes in the, modeling, because you've already done the modeling. But I think that this is a very important factor to consider going forward. Like I say, it could all go away relatively soon, or we could be in a different kind of situation now.
Yeah, that's a great point. Fred, you are seeing that difference between hubs. I would say that's partially mitigated by our forecast looking at specific Western hubs, but still, is an important consideration as we're looking out. I would say, though, that while that's going to have a large effect on the economics of the region, for our resource plan, which basically, the point of it is to tell us how many megawatts we need and when and where. How that is going to change won't really be affected by those gas prices. So I don't think you would expect us to be running our plants for retail load less than our projections, given the need for reliability. Now, as Elaine correctly points out, and as I mistakenly said, that the prices are going to drive that. So if gas prices dramatically increase and market prices go up, then generally that will lead to a higher level of dispatch. that will make a difference on our generation for wholesale sales, which is important economic consideration. And if that happens in an extreme basis, say gas prices triple, our forecasts in the IRP are going to be off in terms of the financial impacts going forward. They won't be off, though, in terms of the resources that we need to acquire, and the size and timing and type. And so, yeah, you're right when we're considering the economics, coming rate impacts, things like that. Yeah, it's huge to be able to correctly incorporate all the movements that are happening in the natural gas market, but generally won't change the actual resource plan that we're creating. Does that?
Yeah, and that's a theme you've mentioned a couple times. I guess I'm just not quite grasping that. The market prices have, they may not affect the resource mix at a given point in time, but over a longer period of time, that's relevant for new resource acquisition, for example. Very high market prices will have a depressive impact on demand, will have a different impact on the cost effectiveness of new resources compared to the existing mix, and so on. So I'm just wondering about the dynamic here. Would seem, and I'm not proposing that I have a great plan for how to address this, but just seems to me that this is a pretty basic thing in the modeling or in the system operation that should show up in the modeling, the resource mix. For example, how will hydro be dispatched in a high market versus a low market? Now, PG has some hydro, much bigger hydro for federal hydro here, but those kinds of effects will happen as well.
I agree, but and again, I certainly take the point that the relative economics will change, and that might tip modeling results from wind to solar. But in general, you're going to be seeing the same results, and you can see that in our modeling right now. We do take a look at higher and lower gas price futures, and because the decarbonization pace is the largest driver here of that resource need, there's virtually no difference across portfolios between those high and low gas futures. If you stretch them further, I don't think that would change either.
Okay, well, I appreciate the discussion, and sorry to have this kind of extended
No,
interaction.
it's important. Like, I do appreciate you bringing it up, and it's like, I think I've said this before, but like remember back in just $2 gas days, it just no one having any belief that they would ever significantly go up ever again, and I think it shows the appropriateness of including a wide range of gas prices in your analysis. Just to go back and to highlight Elaine's point, I think I was describing it incorrectly, and Elaine, you were describing it correctly. Generally, your lower prices will lead to higher dispatch. It is the removal of that carbon penalty that leads to the higher dispatch.
So I don't see any other hands up at the moment. Rainbow, did you have any remaining material that you were presenting?
That is it. Thank you for the discussion.
Okay. I'll pause a moment for more questions here before we move into a break. Seeing none at the moment, I'm going to go ahead and start our break a little bit early. So it'll be 15 minutes instead of 10 minutes, and we'll start back up at 10 o'clock sharp. So you can either leave and come back, or you can just mute your computer and take a break. But 10 o'clock sharp, we'll start up again. Okay, welcome back. We're going to dive right in. For our next topic on the draft portfolio, we have Rob Campbell and Nahit Shah with us. And I believe Seth Wiggins will be introducing this topic for the first slide or two. So I'll go ahead and hand that off when you're ready, Seth.
Yeah, just an introduction. Thanks, Jesse. So I just wanted to talk about this presentation where we are presenting a lot of basically the same portfolio analysis that we talked about in the last roundtable. In discussions about the draft IRP, which we did not submit, we said instead of that, we are going to use the IRP roundtable process to present all our portfolio analysis through the action plan in January when we have otherwise presented our draft IRP and everything included there. And so accordingly, we presented that in our January roundtable, and we have since refined much of that analysis. But many of the slides that you're going to see, the numbers have all been updated and will reflect the current status of modeling, but they look pretty much the same. Accordingly, we're going to move pretty quickly through much of them. The main conclusions from that portfolio analysis around the main questions, such as decarbonization, energy efficiency, CBREs, the main conclusions from January still remain the same. And so we're happy to stop on any of these and discuss the particulars and get into as deep of the weeds as anyone is interested. But if there's not a lot of interest, we're going to move pretty quickly through the portfolio analysis. I would say, though, that similar to in the January roundtable, all portfolio analysis reflect the changes that we made to Colstrip, and from the December roundtable to the January, basically keeping it in the portfolio and having the associated effects on energy and capacity need. Would say, though, that those negotiations for Colstrip exit are ongoing. We're limited in our options, but the negotiations they're literally happening currently. The modeling changes were made to reflect the need to present a plan where we have concrete options. We need to file in T-minus a couple of weeks now. And so we're basically putting the final touches on the IRP right now. And so we need to present a plan that shows our progress towards HB 2021 and meeting meeting emission reduction targets associated with HB 2021. And the action plan is moving us towards meeting that, but we couldn't have portfolios relying on an action, this Colstrip exit, that we don't have a concrete plan for. And so accordingly, modeling results reflect that change. Hopefully that makes sense. And so I'm going to turn it over to Nahit and Rob for this presentation. Please let us know if you have questions on any of it. Otherwise, we're going to move pretty quickly.
Okay, thanks, Seth. I'm Rob. I'll be taking the first section here. So just quick recap. Seth pretty much just described this, but we've presented these presented on portfolio analysis in the past 4 roundtable meetings. Today we'll be covering analysis approach, design requirements, draft results, the preferred portfolio, yearly price impacts, resource build out robustness analysis, and sensitivities. Next slide. Next slide, please. So this is a slide that we've shown a few times, and it is just a high-level conceptual look at our process in portfolio analysis that shows how we move from a set of multiple portfolios that are a fixed set of resource decisions designed to test the impact of specific constraints or resource additions in each portfolio, to a preferred portfolio that is designed based on key insights and common themes identified in the analysis of that set of portfolios. Next slide. This is another one that we've presented a few times, sort of further laying out and defining our approach to portfolio analysis in this IRP. And essentially it boils down to we've tailor designed portfolios and groups of portfolios in this IRP to try to address the key questions, the key planning questions that we see in terms of the pace of emissions reductions, community-based renewable energy, additional energy efficiency and demand response, and transmission. And we designed groups of portfolios to try to gain insights on those key questions and then use those insights to develop a preferred portfolio. Next slide. This is another slide we've seen before. This is just the groups of portfolios that we designed and analyzed. We have decarbonization glide path, transmission, CBRE, additional EE and DR, optimization, targeted policy, and emerging technology portfolio groups. Next slide. Briefly cover some portfolio design requirements. Next slide, please. So these are some key assumptions in portfolio analysis that have remained unchanged since the last roundtable meeting. So I'm not going to describe these in detail, but these are emissions, resource procurement, energy position, contract expiration, RPS, and transmission assumptions that have all remained constant since the last time we presented. Next slide, please. We do have one bit of updated methodology to describe since the last time we talked, and that's our use of generic resources. We have generic resources in the model to allow the model sufficient access to energy and capacity to maintain a reliable system in the face of transmission constraints that we're modeling, which would otherwise result in insufficient resources at some point in the modeling time horizon. So previously, we had a single generic non-emitting on-system resource that provided capacity and energy. It was available starting in 2031 as the default, and we made it available on a case-by-case basis earlier for particular portfolios that were otherwise had insufficient access to resources to solve. The cost of that resource were set very high so that it wouldn't compete economically against the resources that we're interested in looking at, our proxy resources. So as the fixed costs were set at $1,000 a kilowatt year. What we've done now is still a similar approach, but we've refined the approach by using two generic non-emitting resources. One that provides capacity only, it's 100% ELCC, 0% capacity factor, and one that provides energy and capacity designed to represent sort of a generic version of the proxy resources that we have in the model. So it has ELCC and capacity factors that are based on a weighted average of proxy resources in the model. And by having these two resources, the model is able to more finely tune the additions to meet both energy and capacity needs, whereas before it had less granularity with only the option of that single resource that provided both. And now the resources are available starting in 2026 in all portfolios. So we don't have to do the case-by-case adjusting of the timing of availability. All portfolios have access to these resources to utilize as needed, but the costs are still set higher than other resources to avoid competing economically. And we've now tried to base the cost more on a level or more in the realm of the cost of our other proxy resources by pegging it to the cost of our most expensive proxy resource outside of demand response, which is the Nevada transmission proxy resource. So we set the fixed cost at 105% of those. Next slide, please. Okay, so now we'll cover some of the draft portfolio results. And as Seth said, most of these are pretty similar, if not exactly the same as what we presented last time. So I'll be moving through these pretty quickly. Next slide, please. First, we have the decarbonization glide path portfolios. We have 5 of these portfolios, 3 of them that represent on-time achievement of HB 2021 emissions reduction targets. We have a linear reduction, front-loaded reduction, and back-loaded reduction to 2030. And beyond 2030, they're all decarbonized at the same rate. And we also have 2 accelerated decarbonization portfolios that achieve targets ahead of HB 2021 requirements. So we have one that achieves 100% reduction in emissions by 2035, and one that shifts all targets forward by 2 years. Excuse me. Next slide, please. We've seen this graph before as well. This is a visual depiction of the annual emissions associated with each of the glide paths. Next slide, please. Here we have the cumulative emissions throughout the planning horizon of each of the glide path portfolios or the decarbonization portfolios. This is something that we've seen before as well. It still tells the same story that we've seen previously. On the right, we have the 2 accelerated decarbonization portfolios, and we can see that both of those produce lower cumulative emissions from 2024 through 2043 than any of the 3 on-time portfolios. If you look at the 3 on-time portfolios on the left, you can see that the front-loaded decline produces the smallest amount of cumulative emissions. The back-loaded decline produces the highest amount, and the linear decline falls in between. Next slide, please. So these types of graphs should be starting to look pretty familiar to you at this point as well, because I did these types of results a few times, and this shows the cumulative resource build of each portfolio from 2026 through 2030. The general story told by these, again, hasn't changed. There's a slight difference in what we're seeing in the results here because of the difference in having 2 generic resources compared to 1. So you can see now in the graph there are the 2 different generics in there. Key takeaways from this resource build, you can see that the front-loaded decline and the 2-year forward shift in targets both have to start relying on generic resources in 2029, which is earlier than the other portfolios. And the 2 accelerated decarbonization portfolios both have to rely on larger amounts of the generic resources, which is costly. Next slide, please. This is a new presentation of the resource build out results from what we've seen before. So here we have the renewable resource build for each of the decarbonization portfolios from 2026 through 2035. What we can see in this graph is that in 2026, all of the portfolios add the same amount of renewable resources. After that, they begin to diverge. And if we compare against the linear decline portfolio, which in each of the groups is on the left, and it's the lightest color blue, we can see that The other portfolios have to add resources at a more rapid rate through various time periods relative to the linear decline. And starting by looking at the front-loaded decline, we can see that it has to add more resources through from 2027 through 2029 relative to the linear decline. Looking at the 2-year forward shift in targets, which is the darkest color bar on the right, it begins adding more resources in 2027 and maintains that all the way through 2035. And similarly with the 100% reduction by 2035, you could see starting in 2031, it has to add more resources. Some of these differences can be quite large. In 2028, the difference between 2-year forward shift in targets and linear decline is over 1,000 megawatts. And in that year, the difference between front-loaded and linear is over 700 megawatts. So these can be pretty big differences. Looking at the backloaded decline compared to linear, we also see that as we approach 2030, because it sort of starts more slowly and then ramps it up right before 2030, there's a big jump moving from 2029 to 2030. All of these results are to demonstrate that there are potential procurement risks, both with accelerated decarbonization, faster decarbonization through 2030, and backloaded decarbonization through 2030. They can all come with increased procurement risk, but associated with sort of big jumps in procurement in particular years relative to the linear decline, which sort of smooths out those resource additions through time. I see we have a question.
This is Elizabeth. I'm looking at the front-loaded decline having the higher rate of adding build out up front, and I don't see why it doesn't have a lower rate of adding build out later, because it's already put that in.
Yeah, that's a good question. That's a function of how these glide paths diverge and then converge again. So they end up at the same point eventually. So by 2030, front-loaded, linear, and backloaded are all back on the same path. So by adding more in the early years, 2027, 2028, then it actually has relative to linear, I think in probably going from 2029 to 2030, it has slightly lower, it has lower additions relative to linear in those years.
It doesn't show lower, it shows them being identical.
Yeah, they end up identical. The cumulative amount is identical by 2030, because in 2030, they end up at the same place in terms of emissions reductions.
Elizabeth, this is Seth. You're right. It doesn't, well, you have to tease out the marginal. If you look at the marginal additions, you would see a lower change from 2029 to 2030 for the portfolios that went faster earlier. You have to.
It shows it on a different graph.
No, we could create a different graph using the data that's included here that would show that. So if you look at 2029, the second to left, that front-loaded portfolio decline, if you subtracted the 2029 value from the 2030 value, you'd get a small number, whereas the linear decline, you'd get a bigger number. And so you would be seeing the marginal change from 2029 to 2030 be smaller for the front-loaded decline. So the effect that you're looking for, it is here, but it's shown on a cumulative basis, so you kind of have to tease it out. We can create, though, that incremental graph and show you using the same data.
Thank you.
Sadeshna?
Yes, a couple of questions, clarifying questions. One is, Renewable resource includes only wind and solar. Is that right? In this analysis.
Yes, that's right.
Okay, and this renewable resource build out is like these are all new generation resources.
Yeah, that's right. These are
You're
all
seeing, and
incremental
these are
resource additions in Rosie.
okay, and this is like after accounting for any other ways to any other resources that could contribute to lowering emissions, including, let's say, conservation, etc. So this is net of that.
Yeah, that's generally correct. I'd say we account for example, cost-effective levels of energy efficiency and DERs in our load forecast. So that those impacts are seen in the form of lower need numbers.
Okay, and these like map into those need numbers that you're seeing in the load forecast.
Yes, so these additions are determined by the need to, we have a need to replace emitting generation with non-emitting generation. And so these additions are largely driven by our greenhouse gas reduction glide paths. So we have an energy need that needs to be filled, and then a decreasing amount of available energy from existing sources. And so we need to build new non-emitting resources to fill that need. And then we also have a capacity need that goes into this. And these provide capacity as well as energy, but it's really the decarbonization limits that are driving these additions.
Yeah, so I mean, yeah, I was just trying to understand if this, like, if the target set here, like map exactly to those needs that were identified, or like are there, or is this like a part of that?
Yeah, I guess I'm not quite following.
So I'm trying to understand like the capacity and energy needs that you estimated from the load forecast, right? After accounting for DERs and energy efficiency, are the projections of these new renewable resource build-outs, do they like completely map onto those needs that you have identified?
Yeah, what's changing here is with the decarbonization glide paths is the amount that thermals are running. So with the front-loaded decline, there is a reduction in thermal generation for retail sales, which shows a reduction in emissions, but also a corresponding reduction in energy, which increases the energy need which is then filled by these resources. These incremental resources, does that make sense?
Okay, yeah, thank you.
Elaine?
Thanks. I have a follow-up question. I think, Seth, you mentioned that my question was going to be, with these additions, is there a corresponding reduction in thermal generation? And you said yes, but you said for retail sales. And on an earlier slide, I think you'd said that all of the thermal generation is counting in those emissions graphs. And so I'm wondering if you can clarify, is there thermal generation that's not going to meet retail load in the model for which the emissions are not being tracked here, or not included in those graphs, or not, like the constraint doesn't apply to them?
I'm having to check right now, but I am call it 80%, maybe 90% sure that the cumulative additions that we showed on slide 37 are associated with retail load. And so that's where you're seeing the difference. So we do have the total emissions, those are reported in the, or will be reported in the actual filing. But because the economic dispatch is dictating what the existing thermals do, the total generation of those thermals is the same across portfolios, depending on the price feature.
Sorry, let me just make sure I understand. The economic dispatch of those plants is not affected by the carbon constraint. So there might be emissions associated with generating from those plants that is not being constrained, and that you're presuming is associated with some sales to another off-taker.
Yeah, that's correct. So
Okay.
under the direction from staff, we retained economic dispatch as a means of a method of determining total generation from thermal plants. Then when considering decarbonization glide paths, we change the amount that's devoted towards serving retail load, but the total generation and associated emissions are the same.
Got it. Thank you.
Okay, I think we can move to the next slide then. Okay, so on this slide on the right, we have the portfolio cost and risk metrics associated with the two accelerated decarbonization portfolios and the linear decline portfolio. These results, the numbers have changed slightly from the last time we presented them, but like Seth mentioned earlier, the takeaways have remained the same. So we can see that the costs and risks associated with accelerated decarbonization are higher relative to the linear decline portfolio. And some key takeaways associated with that are that achieving HB 2021 targets earlier than currently mandated, as in those two portfolios, lowers cumulative emissions, but increases system costs and risks. And therefore meeting HB 2021 targets as currently mandated best balances greenhouse gas emissions reduction, risk and cost. Next slide. Similarly here, we have new numbers with the same story. We can see on the right that the front-loaded decline portfolio has the highest costs. The backloaded decline has the lowest costs, and linear decline falls in between those two in terms of the on-time compliance portfolios. The key takeaways from these findings, while backloaded has the lowest cost, it also has the highest cumulative emissions. Both front-loaded and backloaded have procurement risk associated with those more condensed resource additions relative to the linear glide path. And therefore, our key takeaway here is that we should use the linear reduction glide path through 2030 in the preferred portfolio and as the default in all the other portfolios that we present here. Yes, Elizabeth.
It seems like the assumptions you're making would heavily influence whether it costs more or less when you're front loaded or back loaded. And I'm concerned about the possibility that over time, the more desirable spots for putting the renewables could be taken up, and the low hanging fruit will be taken. And then you'll be stuck in the later years trying to get sites that there's more competition. How does that compare with the assumptions you're making?
I can take this, Rob. That's a great question. And I think it goes beyond just the geography, in that competition for renewables will be fierce as these carbon targets start to bind. There are some within PG that say that kind of commodity crisis rights itself in a few years in general, and that we should be fine going forward. There are others that are extremely pessimistic. It's uncertain, but I think it's increasingly plausible that what you're saying is correct, that the uncertainty around supplies, materials, labor, geography, all of that, transmission, suggests that earlier action is warranted. We do make an attempt at evaluating different resource trajectories based off of technology costs. So, we assume, following historical developments or historical reductions in renewable costs, that the costs will continue to decline, but we do evaluate higher and lower technology cost trajectories. But it's, as you say, it's plausible to think that maybe we should be looking at cost increases going forward. We could do that. We could change the discount rates. It would do the same effect. The analysis that we have, I guess in the extreme, if you show renewables, say, doubling in cost every year going forward, the model, it's clearly going to tilt the model towards earlier action. So you would see a change in these graphs towards the front-loaded decline being a more cost-effective option. So it really is, the impact is really just a function of that assumption. In this portfolio analysis that we have, we've been sticking to those earlier assumptions, though we'd be interested to hear if you thought, the NREL projections of cost declines should be changed in some way. We could certainly do that and start looking at different trajectories here.
Well, I'm hearing that in some states and Washington counties that they're actually passing laws to not allow more solar into some of the eastern counties and also in the Midwest. So it would tend towards not using the assumptions that you mentioned first and going with the ones that you mentioned otherwise.
Yeah, I think they did that in Marion County too. Okay, yeah, we appreciate that feedback. We can take that back and see what other types of analysis we can do here.
Thank you.
Thanks, Seth. Okay, I think we can move to the next slide. So now we'll get into the transmission portfolios. We've presented on these before. We have three subcategories of portfolios here: informational, transmission diversity, and transmission timing. And these are all of the portfolios that we looked at related to that. Next slide, please. So this shows the resource build-out results through 2030 for the informational transmission portfolios, which are the unconstrained transmission portfolio, which does not enforce any transmission constraints. And this essentially is how portfolio modeling was done in the 2019 IRP. You can see large amounts of wind addition and no CBREs added. In the no upgrades portfolio on the right, we can see that it adds all available CBREs and has to rely heavily pretty heavily starting in 2029 on the generic resources. Next slide, please. So using the amount of generic resource build in the no transmission upgrades portfolio, we can try to estimate the magnitude of potential transmission upgrades that might be needed to allow access to sufficient resources for the model to solve to create a reliable system. That's what we have in the table on the right. The numbers are a little different from last time because we now have the two different generics, but it tells the same general story. By 2029, we see need to build transmission with 159 megawatts showing up. By 2030, it grows to between around 540 and 770 megawatts, and then just starts to grow pretty rapidly from there to over 2,000 by 2035. So some of the takeaways from here highlights that transmission needs are rising by 2029 at the latest. The transmission need is significant and required for PG to reliably decarbonize to meet 2030 targets. And looking at these really large numbers that you see later on in the analysis, you can see that transmission is the single largest factor impacting the economics and timing of resource additions in this IRP. Next slide. Here we have the cost and risk metrics for the unconstrained transmission and no upgrades portfolios. You can see on the right, with no available transmission upgrades and heavy reliance on the generic resources, portfolio costs become very high. The number itself is really a function of the cost of those generic resources and the design of those generic resources. So this is more of a directional result, but it shows that the costs grow substantially when you don't have access to the transmission upgrades. And the unconstrained transmission costs are relatively low compared to this the no upgrades portfolio, as well as other portfolios. So showing that if you're not considering the transmission constrained reality that we're living in, you're going to underestimate the costs associated with acquiring the resources needed. So some of the key takeaways here, in addition to these differences in costs, one of the key things that we note is that without the transmission constraints, CBREs are not selected. So showing us that introducing the transmission constraints is one of the things that drives the competitiveness of CBREs in this modeling environment. Next slide, please. Here we have the resource build out for the transmission diversity portfolios. On the left, we have unconstrained SOA, which allows the model unconstrained access to the South of Alston upgrade starting in 2027, and unconstrained SOA plus on the right, which allows that same access to the SOA upgrade, but also allows access to 400 megawatts each of the Wyoming and Nevada transmission proxies. We show these resource build numbers out a little further than in the other portfolios to show that if we're only looking through 2030, even all the way through 2035, these resource builds are the same. The model is relying heavily on SOA upgrade, but if you get far enough out you can see in 2036, more clearly in 2037 and 38, the model starts to add some of the transmission expansion proxies, eventually choosing to rely on the high capacity that they provide farther out in the future once ELCCs of other more local or Pacific Northwest resources begin to drop off. Next slide, please. So here we have the cost and risk outcomes of these two portfolios. We can see that they are not wildly different from one another, but unconstrained SOA Plus does have somewhat lower costs relative to unconstrained SOA because it is able to take advantage of those transmission expansion options, showing us that increasing access to the current Pacific Northwest proxy resources through BPA is a sufficient condition to decarbonize reliably, but that investing in additional transmission options beyond the BPA choices can reduce costs. Next slide, please. Here we have the resource build out results for the transmission timing portfolios. These are generally unchanged from the last time we presented these results. Next slide, please. Here we have the cost and risk metrics of those portfolios on the right. Again, slight changes in the numbers, no change in the relative ordering of the outcomes here, and no change in the takeaway message. The key thing to see in this graph here really is that on the right, we have SOA in 2027 plus, which has access to south of Alston upgrade, as well as the Wyoming and Nevada transmission expansion proxies has the lowest cost and risk, suggesting that the preferred portfolio should pursue all opportunities to increase access to current proxy resources in 2027 and include access to the new transmission options in 2026 to minimize both cost and risk. Next slide, please. Next, we will cover the CBRE portfolios. Next slide, please. Here we have the resource build through 2030 for the CBRE portfolios. Moving from left to right, we have increasing amounts of CBREs in the model, and you can see that showing up in purple. Default CBRE and CBRE optimize have the same amount. With default CBRE just including the full amount of CBREs, CBRE optimize having the opportunity to add up to the full amount, which the model is choosing to do. Next slide, please. So here we have the cost and risk outcomes, as well as the PCBI outcomes for the portfolios on the right. This is another case of small changes in the numbers, no change in the ordering or the key takeaway as you move from left to right in the NPVRR and semi-deviation of NPVRR graphs. You see that as you move from no CBREs up through increasing amounts of CBREs, costs go down. Similarly, as you add more CBREs, the PCBIs provided by each portfolio go up. So we see that selecting 100% of CBREs both maximizes the community benefits and reduces portfolio costs, leading us to the key takeaway that the preferred portfolio should include 100% of CBRE potential to ensure the least cost portfolio and maximizing community benefits. Next slide, please. Next, we have the additional energy efficiency and demand response portfolios. These are somewhat different from what we saw last time because the portfolios were still a work in progress as of the last roundtable. So what we have now are fully refined list of portfolios for this category, runs from 0 NCE, which is no additional demand response or energy efficiency available, up to moving through 25 average megawatts of EE through 2030, 50 average megawatts, 60, 70, and then optimize energy efficiency, which has access to the full 70 average megawatts through 2030, but is not forcing it into the model. Next slide, please. Here we have the resource additions through 2030 of these EE portfolios. You can see the moving from left to right. You can see the amount of EE added in blue, sort of near the bottom of the stacks, increasing up through optimize, and then well, I guess increasing all the way through to the 70 average megawatt portfolio. Next slide, please. So on the right, we have the cost and risk metrics for these portfolios. And what we see here is an interesting pattern where we start on the left with the least amount of EE with 0 in the 0 NCE portfolio. It has I guess then as you start to add EE, we see that cost decline. So as you move to 25 average megawatts and then up to 50 average megawatts, portfolio costs and risk decline. However, at a certain point, as you continue to add more EE into the model, costs start to increase, demonstrating that there is potential to lower portfolio costs with EE, but there is sort of a diminishing marginal return there, and at some point the costs start to outweigh the benefits and costs increase. So given this finding, in a world with transmission constraints, additional EE could be an effective strategy to decrease cost and risk. However, there is procurement risk and cost pressure associated with additional quantities of EE, and that's going to be covered much more thoroughly by Nahit in the yearly cost model that he's going to get into in a little bit. As a result here, our takeaway is the preferred portfolio should include the cost-effective levels of additional EE, but no additional non-cost-effective EE. Yes, Elaine?
Thanks. And so I just want to unpack that a little bit. The preferred portfolio includes the 0 NCE level of energy efficiency from this graph.
Yes, that's right.
So you're not interpreting a lower net present value revenue requirement as an indication of cost effectiveness. When you say cost effectiveness, you're using a different, whatever the Energy Trust shared with you in their forecast.
Yeah, I guess that's the definition of cost effectiveness that we're using here. You could think of, the fact that it's lowering costs. So in the row Z world, in the portfolio analysis world, you could call, I guess they're showing up as being cost effective, but we wouldn't want to use that term because that would, create confusion with the standard use of that term. So we do see that they have the potential to lower portfolio costs. But there are the other considerations related to the timing of impacts of those costs, which Nahit's going to cover. So this, this provides one piece of information about it, but it doesn't provide all of the relevant pieces for decision making regarding these resources.
Okay. So it's just so that it's clear, because when I was trying to interpret sort of an earlier version of this slide, I think from prior roundtable, I was confused by the use of the phrase cost effective, because it looked like was not including what you might consider to be cost effective and from an IRP modeling perspective. And it ideally the IRP modeling and maybe the energy trust cost effectiveness analysis would be iterating towards the same conclusion. But I'll reserve further questions till we see the content you're kind of describing around annual costs if they come up. Thanks.
Yeah, I would just add that that confusion has been felt in many rounds of review of the draft IRP so far internally as well. Just the framing of non-cost effective from ETO to our analysis. Like we need better words for that for sure. And I would just add that, you know, if we were using the same inputs for the determination of the cost effectiveness of these resources, then if the models are working correctly, you would see the same result. The problem we've identified is that the lag between when we provide those inputs to ETO's calculation is such that, you know, a major policy change has happened, changing the estimated avoided cost of capacity and energy. And so the capacity change it's pronounced. It's moving from a emitting resource, a simple cycle, to a non-emitting resource. It is real, but the energy is the real driver here, in that it's not replacing a market, it's replacing a steel in the ground plus transmission option. And so when you're evaluating, as Rosie does, those resources against other options that the utility is facing, then the actual avoided cost, the avoided resource that energy efficiency or any other resource could avoid is substantial. And so we're trying to highlight, both in the roundtable and in the document that we're going to file here at the end of this month, try to highlight this difference and the potential discrepancy that's showing up in the models based off of current evaluation methods.
Yeah, I think it's really excellent that you can see that so explicitly. I mean, I would expect that in an environment of you know, a really strong carbon policy, that the value brought by energy efficiency would increase potentially substantially because of the cost of the alternatives. So it's cool that you're seeing that in the analysis. I'm just kind of scratching my head a little bit about why that wouldn't be considered ideally cost effective. So
yes, in IRP terms, when you're looking only at this long-term system cost, yeah, it's absolutely cost effective. But the data was labeled when it was coming from the ETO, and so they divided it that way, and so it made sense for us at the time to keep the label. Maybe it would be better to label, instead of non-cost effective, you know, additional potential, something like that. But yes, from a long-term system view, this is a better option than everything else in our constrained world.
Okay, thanks. Next slide, please. All right, here I'm going to pass it off to Nahit to talk about the preferred portfolio.
Thank you, Rob. Good morning, everyone. My name is Nahit Shah. I'm an analyst on the IRP team, and this next section is largely similar to the presentation I made about a little over a month ago. And so we'll be going through these relatively quickly. The takeaways and sort of the direction is roughly the same. There is more information based on some of the feedback we heard previously. So happy to dive into that as needed. So with that, Shadia, if you could move to the next slide, please. So to kind of summarize, Rob's gone through all these different combinations and sort of groups of portfolios that try to address several questions, associated with different elements in this IRP. And what we've essentially done is taken all these insights and kind of try to merge them together in a way that can help us understand what is the best option, in terms of developing a preferred portfolio. And so what we have done here is essentially looked at all these 39 portfolios and sort of extracted these sort of key insights. The first one of which is that, in trying to figure out how we meet the 2030 targets of HB 2021, we've kind of settled on the fact that the best way to balance risk, cost, and greenhouse gas reduction is to choose a linear reduction path. It makes sense to choose 100% of CBREs to maximize community benefit. But what we also saw was that given the transmission constraints, CBREs can help offset future transmission, especially because they're largely distribution connected resources. And so you see that there is both an economic incentive to have CBREs, and in addition to that, we have this push towards maximizing community benefits. So CBREs are able to provide both those values, and therefore selecting 100% of the CBREs should be a central part of the preferred portfolio. Additionally, as we just talked about, we are incorporating, as you can see, it's in quotes with a small typo there, but effectively the cost-effective levels, which, again, the cost-effective, the way we define it here is based on how the Energy Trust and the DSP previously evaluated these resources, right? And so those resources are included. Any additional resources that were not deemed cost-effective at the time are not included. And we think that that's the best way to minimize cost and risk because of a risk element that I will dive deeper into associated with near-term cost pressure in just a few slides. So we can talk about that in just a bit. Regarding transmission, there are kind of two pieces. The first of which is to understand how we can alleviate transmission constraints closer to our system in a way that increases access to sort of our traditional proxy resources. And that comes in the form of 400 megawatts of congestion relief on the south of Alston Plain. And that will ensure that we are able to reliably meet our 2030 needs while minimizing cost as well, and without relying necessarily on potentially emerging technologies that aren't yet proven. We also saw that adding new transmission options do provide benefit in the long term and can provide cost and risk benefits in the short term. So while they might not be necessarily required to meet reliability for 2030, it is definitely helpful to minimize cost and risk. And so that's the driving force to make sure that we have additional transmission options. And that's where the 400 megawatts of Nevada and Wyoming transmission come from. And so we combine all of these. And when we put that together, we kind of get our preferred portfolio, and we realize that we're pretty much in this space where we kind of have to do almost everything we can. And so if we go to the next slide, we see we see our resource build out. So this slide should be familiar from the last roundtable. We have added some more information here. So you will notice on the table on the left, there are 4 additional rows after the contract extension. Those 4 rows are Clearwater Wind, Wasco Solar, Christmas Valley Solar, and 4-hour battery. And these represent the actions that are a result of the 2019 IRP coming through the 2021 RFP. Right. So these are actions that are kind of underway. Clearwater has already been signed, so that project has a name, whereas the other 3 are expected actions, and we don't have any final decision on them yet. And so these 3 resources, Wasco Solar, Christmas Valley Solar, and the 4-hour battery, are effectively proxies to represent the expected actions of the 2021 RFP. And so those are represented here and are a little more transparent on the graph on the right at the very bottom. In addition to the build out of the of the preferred portfolio, for informational purposes, we've also added 2 rows at the bottom that talk about the cost-effective energy efficiency and demand response that are included. The energy efficiency amounts here represent the incremental amount starting in 2024, whereas the demand response represents sort of the overall size of the demand response portfolio in that year. And so we have these to show that yes, energy efficiency and demand response are part of the whole solution, while even though they're kind of accounted for at the load forecast level and in the needs analysis, they are part of the solution. It's just a matter of where we are accounting for them. And the previous slides that Rob was just talking through and we had a good discussion around is focused on the additional energy efficiency and demand response above these levels. And we're saying that we are not pursuing any of those for the reasons of cost, of near-term cost, which again I will describe in a few more slides. Right. So with that, to take a more detailed look on the build out of the resource build out of the preferred portfolio, we had some feedback last time that we wanted to see sort of the entire build out through the planning horizon, and this is a look at that. And essentially, I think you know, the takeaway is sort of the same, and we've kind of mentioned this a few times, both verbally and in some of the other graphs. There is, in the long term, uncertainty around emerging technologies and other transmission solutions that may appear, and the generic is meant to sort of represent what those could be, right? And so you can imagine in a world where, you know, we figure out this really low cost, reliable capacity and, you know, high energy factor resource, you would imagine that the quantity of the resource on the generic would start reducing to reflect different characteristics, and the associated costs would also change based on the different characteristics. So there is definitely a lot of uncertainty in the long term, and an area that I think as a group it requires a lot more discussion of what resources those could be, or what strategies those could be, whether that is unlocking additional transmission that could offset it, or it's emerging technologies that can replace it. But yeah, but in the short term, there's definitely more concrete direction in how we have these resource actions impact our HV 2021 goals through 2030. I think there's a question, but I'm just gonna take that question after the next slide. So if we could just move to the next slide here. Yeah, and so this is effectively a table version of the previous graph, and has most of all of the same elements, and so for those of you that are more curious about specific numbers, I'm going to kind of leave this here for a minute, and I'm happy to take questions at this point. I think I saw Kim's hand first.
Yeah, this is just I think a simple question, but in the slide before, it looked like you had, it was hard to tell between the different colors, but it looked like you actually had offshore wind showing up on that, but I thought it sounded like it wasn't going to be showing up, and it is not on here. Can you just clarify that?
Yeah, there shouldn't be any offshore wind. So I know that the blue colors can seem a little can blend in a little bit, but there isn't any offshore wind.
Okay, thanks. And I'll have more questions, but
to follow up with that answer, Kim, there's no offshore wind as a function of the preferred portfolio not having access to it. So as we show in one of the later portfolios, when you allow access for offshore winds, the model takes it.
Gotcha.
Given our assumptions about the performance and cost of the resource. We don't make it available until 2032, so this isn't going to be a resource that gets us to 2030, which is why we have let it not be in the preferred portfolio, just because we wanted to either have the resources that we feel confident to get us to 2030, given the modeling assumptions, or just the generic resources after that. But I think our portfolio results suggest that it all depends on the input assumptions that you put into it, but offshore wind, given our current understanding, is an attractive option, and the more of it we get, the better.
Okay, thanks.
Pascal?
Yep, Nahid, were you calling on me? This is Bill Pasco.
Yeah, hi.
Hi. I have a comment and then a question, and neither one will take very long. The comment is that if you go back a few slides, the slide that shows the 5 kind of planks of the preferred resource plan, one more back, please.
Mm-hmm.
You know, and it says access to Nevada and Wyoming transmission. I think we know, as part of this process, you've talked about these as being proxy projects or proxy resources. So I think you'll want to be careful as you put together the filing that you're going to make with the commission to be clear that they are in fact proxy resources, and you haven't necessarily determined that Wyoming and Nevada are the only places you'd look for transmission market access or transmission access to, you know, renewables that would offer some diversity with the resources you could get on the Bonneville system. So that's my comment. My question is, and I think I know the answer, but I'm just verifying. The Nevada and Wyoming proxies that are in here, those are based on, what's the cost basis for those? Is it new builds, or you know, are they generic projects, or are they specific projects that somebody else is developing, or where do the costs for those come from?
Yeah, I can start with that, and I think a couple of people might jump in. So there are sort of 3 cost elements. The first is that, let's take Nevada, for example. We are thinking that there will be Nevada solar at the end of the line. So there is the cost of the solar plant, right? So there's that proxy cost. Then there is a proxy cost associated with the market access that the transmission kind of enables, because we have access to the region, which might, you know, because they are a different region, different timing, we might be able to get some diversity and able to get some market access through that. So there's a cost associated with that, which is assumed to be the cost of a 6-hour battery. And lastly, there's the cost of transmission. The cost of transmission is based off of a paper that and a couple of other sources that our transmission team kind of put together. But it is essentially the cost of a new build, but it kind of assumes that we are buying into it. So the assumption is that someone somewhere is building for it at this price. But we don't have to necessarily wait for the same amount of lead time. We would have to pay for the same price, though, if that makes sense. And I'm happy for Seth or anyone from the transmission side to jump in and add to that.
No, I think that's right. The costs we discussed a couple of times in the fall, and we can follow up again with the source of that data. But to your first point, I think you're absolutely right as well. And we're doing everything we can to try to make that point as clear as possible. We've got a team that's looking into the actual commercial operations or commercial opportunities out there. And we want to be as clear as possible to the commission that we are treating the proxies in IRP analysis as just that. These are general characteristics that we think are plausibly found in the market and don't represent actual projects or actual lines that we're looking at right now.
Okay, thank you.
Tim, I saw your hand go up again.
Yeah, thanks. Stay on the slide if you would for a second. Forgive me if I'm being dense, but I think part of what I'm still trying to wrap my head around is the sort of the difference in use, or sort of the value of modeling and considering the proxy transmission as compared to offshore wind and the associated costs and impacts there. And maybe you just said it, and that part of this has to do with the Nevada and Wyoming transmission is sort of not something that is a project on PGE's action plan, or activities that you'd be actually engaging in or paying for, but that it might that might be available. Whereas is part of the difference that the offshore wind doesn't function like that. It's something that could be part of the action plan, and so there are other reasons for not including it. I guess I'm just sort of trying to make sure it's really clear that I understand why the impact of including the transmission proxy versus the impacts of considering offshore wind and those associated transmission aspects.
Yeah, that's a great question. So the offshore winds is tricky for us because technically it's not an option for us right now. And a lot of things have to happen. That's true with transmission as well, but we think it's reasonable to expect that in the market and create a plan around that. Now, it's important to clarify that action plan is just through 2028. And so some of the offshore resources, we think the best available data says, it's not going to be there until early 2030s. And so, whether the action plan or, preferred portfolio was dependent on offshore's availability or not, doesn't really change things. It could, the assumptions that you give it could potentially lower costs in the out years. But if 100% of parties here thought that, yes, you absolutely should make that available for the preferred portfolio in 2032, we certainly could, but I don't think it would change that much. And when we get out past 2030, it's there's some judgment involved as to what level of specificity we have. If you look at the 2019 IRP, we had upwards of a couple thousand megawatts of Southeast Washington winds in 2048. It's just not a very helpful statistic. It's informational, it's directional, but whether that was Southeast Washington wind or Montana winds, we're not really gaining much from that. And so we use judgment for the preferred portfolio to just rely on those generics to be more of an identification of need, a plausible identification of the resources that we would have to get, assuming that there's no major technological breakthrough. But we could have included offshore, and it's just a judgment call there.
And I guess thanks for that, Seth. And I wondered whether there are any other impacts in particular with regard to avoided costs, if those are included, if offshore wind was included, and whether costs associated with that inform other avoided cost decisions based on that avoided cost.
That's a good question. So because the avoided costs are based off of, in most applications, the calculation is either for the energy value is either from market prices or from a near-term resource build. And so, if the model's picking offshore winds, then that means that in that year it's available, it's more cost effective than that other resource. So yeah, if avoided costs were based off of resource costs in 2032, it's possible that it would change the avoided costs that are applied elsewhere. But I think in this context, or in the context that we only rely on those near-term resources, I don't think so. Again, confidence isn't 100%, but it's above 80.
Okay, thanks, Seth.
I think there's another hand, JP.
Hey, thanks. Just two quick questions for you. One on the transmission here in the preferred portfolio. Given what we know about transmission constraints coming into your BAA, is the access to the 400 megawatts of Nevada or Wyoming wind, is that linked to the relieving of congestion getting into your balancing area? Does it assume that that's the current that's taken care of some other place? And then I have another question.
Yeah, just to make sure I'm understanding that right. You are asking whether the 400 megawatts of congestion relief on south of Alston effectively enables the 400 megawatts for Nevada and Wyoming. Is that right?
Yeah, I mean, just given what we know about getting from Boardman into your territory.
Yeah. No, these are assumed to be separate. So in effect, it is 1,200 sort of megawatts of capacity or like of transmission capacity, if you want to think about it that way. 400 megawatts available to sort of the traditional proxies that arise from the congestion relief over south of Alston, and then 400 megawatts each from Wyoming and Nevada. And yes, there is definitely difficulty in the last mile, getting over BTS system. But I think that is assumed as like an element that can be addressed, but not by the 400 megawatts of south of Alston. That is separate. So does that answer your question?
Yeah, thanks. Just wanted to clarify that. And then sorry to make you scroll around. If you could go back up to the that great table you guys had of the one more. Yeah, perfect. Thank you so much. Where in here would the hydro be? Is that under the contract extension? Is that under a generic cap? And then the follow on to that is, if hydro is not in here, how is that playing into what you're looking at? We're seeing bilateral contracts with Puget Sound Energy for long-term hydro. And I'm wondering, if there's capacity additions that are necessary in the next RFP that you guys are looking at, where does that bilateral, that doesn't fit into RFP, where does that bilateral fit in?
So it fits in within the action plan, and so Seth will definitely be going over that. And so one, similar to the 2019 IRP, a sort of first step in addressing capacity needs is to see what's available in the bilateral market and see if we can get a good price on capacity. And so that is an avenue in which capacity needs will be addressed. Those are not necessarily reflected in the same way in the preferred portfolio, though the contract extension is sort of generic and could be representative of a hydro contract as well. And so we do expect that some of our non-emitting contracts worth 200 megawatts of capacity would sort of extend, and that could have some portion or all of it could be hydro as well.
Okay, so the existing hydro may or may not be part of the contract extension. That's just a generic contract extension, and then there's nothing in here around the preferred portfolio trying to select regional hydro as a resource.
Yeah, I would put sort of hydro in the same bucket as offshore wind, right? Like these are projects that
except that it exists.
Yes.
And people get actual contracts for it right now. Yes, long-term.
Yes, most certainly. And the way I think it would manifest is you would see it sort of interacting with these other resources. So you can either think of it as, it's coming on later on to replace the generics, or it would be competitive. So theoretically, if we got a hydro bid in the RFP, we would definitely pick it, right? Like the preferred portfolio is in a sense directional, and it's the bids that really determine what the resource build is going to be through the RFP. So the preferred portfolio, in a sense, does not necessarily dictate that we will actually have 227 megawatts of wind. And so I would think that would be the right kind of interaction, where if we see the bids, we would include it in our analysis and determine at the time whether it made more sense to go after hydro or whether it would make sense to maybe stick with wind or something else.
Thanks, Nate. I would also add that there's this difference between the preferred portfolio, which talks about these resources that we think are the best combination of cost, risk, community benefits, and emission reductions. These are megawatt values, but when we go for the when we move to the action plan, which we'll be discussing later, we turn from what we think of as like preferred resources, we turn to system needs. So the RFP is going to be focused on meeting those system needs, and as Nahid alluded to, for the capacity especially, but also energy, our needs should be updated when the or after any sort of bilateral action. So if we're able to re-sign any of the contracts that are expiring or potentially get other regional partnerships, those should all be incorporated into RFP targets, such that when we're doing the RFP, you have the most up-to-date information. We're not under or over procuring for those. But those contract, a hydro contract in the bilateral market is an incredibly attractive option given the capacity and non-emitting nature. And so we definitely want to pursue all that we can in the bilateral market and then update the RFP accordingly.
All right, thanks. I appreciate the distinction between what get modeled and for the preferred portfolio and the action plan. So that's great. And I just would say, Seth, I mean, I'm sure you're gonna get to it later, but that's one of the things staff will be looking for, is kind of like a repeat of 2016, what actions were taken to go to the bilateral market to figure out what's out there. So thanks.
Yeah, that makes sense. And I guess I'll just add that we'll be talking later about the RFP. We're going to attempt to do things concurrently, the IRP docket and the initial phase of the RFP. And so it'll be pretty critical that we are updating resource needs throughout that time. So we're given the most accurate information.
I will just note one thing here on this table. I think there's a small typo. So the resources, all resources above the cost-effective EE and DR, I think, their numbers sort of start in 2028. Those should be in 2026. I think they just got shifted out a little bit. So we will update the slide when we send it out. But just note that actions are being taken in 2026, and in alignment with sort of the previous graph, which showed that. All right. With that, if we can move to the next slide, please. So that kind of brings us to the cost and risk metrics of the preferred portfolio. So we did see that like an unconstrained portfolio and a portfolio that is completely unconstrained by transmission, can go as low as about $19 billion. And we see that like our transmission, definitely has a significant impact in how in the cost of the preferred portfolio and the actions we have taken to minimize those costs. So even though it's a least cost, least risk in how we are thinking about it, it is definitely increasing costs over time as a function of transmission itself. So that comparison is really evident, and you can also compare it to some of the other portfolios to sort of draw some basic insights on how it's impacting cost relative to those assumptions. But we believe that this is sort of the right combination of resources. Next slide, please. This slide is not different. I mean, the numbers might have changed just a little bit, but the overarching takeaway is that HB 2021 requirements are far more stringent than the renewable portfolio standards that are on the books. And so the RPS requirements are now essentially redundant because the recs generated from complying with HB 2021 are far more than what would be needed to meet RPS obligations. So there is sort of, you know, in moving in the direction of decarbonization, we've taken a very large step here, and it's kind of evident in the rec generation. And we see that the RPS is definitely you know, a standard that no longer influences resource actions in this IRP. Or actually any IRP moving forward, because the HB 2021 constraints will always be more stringent. Yeah. Next slide, please. All right. So at this point, I'm happy to pause on questions associated with the preferred portfolio. And once we are done with that, we can move into the price impacts, which is a new element within this IRP. All right, if we can move to the next slide, please. So in response to some of the discussions that we've had with stakeholders over the last couple of years and direction from the UM 2225 docket for the Clean Energy Plan, PGE has taken steps to develop a new tool. We call that ART, or Annual Revenue Requirement Tool, and the ART effectively helps us both understand and compare yearly price impacts of different portfolios. And so we include most of the same elements as we do in the rest of the IRP, but there is a certain lens through which you need to look at the ART results. There are lots of limitations and caveats. This analysis is definitely helpful, but you know, if misinterpreted, could lead to a significant amount of confusion. And we want to make sure that we are able to use these results in a manner that is most productive to the entire group. And so I'm going to go through a few of the limitations and the assumptions first. And so essentially setting up the frame through which you should review these results and how they are helpful, and what are the things you shouldn't be focusing on in terms of their impact and in the real world, right? And so starting with some of the limitations here, I want to stress that the ART, similar to portfolio analysis and the remainder of the IRP, is focused on sort of the generating resources. So we're looking at costs of existing resources and new resources and all their different cost elements. We do not include costs such as grid modernization, administration and general costs, wildfire mitigation costs, T&D costs. For T&D costs, it's just a nuance. Wheeling costs associated with accessing a resource are included in the IRP. Transmission costs associated with accessing a resource, so for example, the Wyoming and Nevada transmission costs, are included in the IRP. However, you know, sort of day-to-day transmission maintenance that might be required, you know, part replacements, reconductoring, that sort of standard business is not included here. So sort of you want to think about the transmission costs in the IRP specific to the resources, and these T&D costs is sort of generic that impact the entire company. And so we don't include these, and there are more costs like these that we do not include. The focus again is primarily on generating resources and their related costs. We do assess yearly price impacts, but these price impacts, you know, are not allocated to customer classes. They are not accounted, they do not account for, you know, these other costs that we just talked about, and they also account for proxy costs, right? So we had discussions earlier in the year and over the last couple of years of using public sources. So we're using NREL's annual technology baseline as a public source, public sources might not be reflective of the bids that we get. And so these prices might not be reflective of the actual costs that customers will incur. So all of these things kind of show that these price changes do not actually show you what how customer prices would change. And so it's a helpful analysis when you're comparing portfolios, but if you're thinking, oh, is the price going up by $10 a megawatt hour, that is not a great takeaway. That would be inappropriate given the limitations of the model and these sort of caveats that we are walking through. Additionally, because of the scope, we are only accounting for a smaller fraction of the total costs that the company bears. Applying percentages to these numbers would not be representative of the actual change in customer prices, right? So if generating resources are worth 10 units and they change 10%, that's one unit of change, whereas the entire company might be changing by 10%. That is 10 units of change. So you don't want to apply these percentages based on the fact that it's a smaller number, and that can lead to misleading sort of interpretations and takeaways that may not be appropriate. It might seem to inflate how much costs are actually changing, and may not reflect actions in the rest of the company that either increase or decrease costs. Lastly, we've mentioned this previously in portfolio analysis as well, but it's true in the yearly prices as well. Generic resource costs have a large impact on yearly prices, right? So if we can get offshore wind or something like that to offset it in future, the real cost from those projects should be incorporated, but those may not, that they may be lower or higher than the generic resource, and we just don't know yet. And so we need to keep that in mind as we think about prices, especially post 2030. All right. With that, we can move to some of the assumptions on the next slide. So just so that everyone is on the same page here, all costs are in nominal terms, so they include inflation. The model uses proxy resource and their associated characteristics. So we have, for example, a resource with say 25% capacity factor. In reality, the resource comes in with 27% capacity factor. That would affect the prices, its generating profile and things like that. So those will impact sort of customer prices. But we in this model are using only the proxy resources. We include the impact of wholesale market sales and market purchases on an annual basis, similar to how we work with those in ROSI and in the intermediary GHG model, which Thomas has explained previously. Our base assumption for some of the modeling work here is that the ownership structure would be a 50% PPA and a 50% PGE ownership. However, we have varied the ownership structure all the way from 0% PPA to 100% PPA in 25% increments. So there are 5 such ownership structures, and those essentially can help you understand how ownership affects near-term versus long-term costs, and those findings are also evident in the following slides. A couple more to go over here. For the 2021 RFP, we have included Clearwater from 2024 as expected and as announced in the press releases. And we have also assumed 100% PPA for the remaining 2021 RFP resources. So if you just think back about 4 or 5 slides where I mentioned the 3 RFP proxy resources, Wasco Solar, Christmas Valley Solar, and the 4-hour battery, we are assuming 100% PPA for those resources. Consistent with the portfolio analysis, we assume coal strip exit in 2029, and we make sure that all our results are in the reference case scenario. So they use reference need futures, reference price futures, and reference cost futures. One really important note to make is that our current treatment of energy efficiency and demand response is reflected as is here. And so it assumes that these measures, these technologies are not financed, and they are essentially 100% of their cost is borne by customers in year one, consistent with current policy again. And so we'll talk about this policy impact in again just a few slides, but that's really key as we think about the rest of this. So before we dive into the results, a little bit on sort of why we are doing this and how we are doing it. So if you could move to the next slide, let's get to the why. So we have created ART in addition to ROSI because of a few things. So there are sort of two key areas in which we kind of think about this, costs and benefits. So in terms of cost, ART and ROSI have the same categories of costs. So they include existing and new resource costs. They include the fixed costs, the variable costs, and the integration costs. However, ROSI looks at these costs on a levelized basis because it's discounting them over the planning horizon. So on a present value basis, it's fine. But for a yearly price impact, from a yearly price impact perspective, it matters when those costs hit the books and when customers would have to incur those costs. And so the ART effectively accounts for the ownership structure, which accounts for the impact of taxes and the relevant years in which the tax credits hit the books. And so we account for that in ART. And so the costs are essentially the same components, but the way they're spread out across the years are different between ROSI and ART. On the benefit side, ROSI accounts for all resource benefits, everything from resource CBIs to flexibility value and energy value. Whereas in ART, we are only focusing on the monetary benefits that customers receive from the resources that exist, right? And so the monetary benefits are limited to wholesale sales. So customers do not actually receive reduction in bills as a function of flexibility value or RCBI, or even the energy value. They only do receive reduction in their bills as a function of a reducing revenue requirement from wholesale sales. So that definitely has an impact, and that is something we've accounted for here. I think we can, I think this might be a good time to take some questions. I think Kim, I saw your hand go up first.
Thank you. Just so I understand, in the ART version, if what we're trying to show is the sort of annual impact to customers, is this is the impact of energy efficiency captured in that? And if so, the question around the costs and risks of higher energy efficiency, are the benefits that customers get reflected here if those higher energy efficiency levels were accomplished or approached?
Yeah, absolutely. And I'll get into this in more detail in just a bit, but essentially energy efficiency is offsetting a more expensive resource, right? So you see the amount of generics that are in there, and it's kind of offsetting the generic in many cases, or it's able to push out, a battery installation by 3 years when we expect the battery to be slightly cheaper. And so it's able to get sort of that arbitrage in installing the battery is also attributed to the energy efficiency. So those benefits are seen in the reduction in fixed costs of the portfolios, and those will be evident in the following slides.
Okay, but I guess the question I'm trying to get at is, well, or just then maybe we'll see it in the next couple slides, is understanding whether the beyond the ETO cost effectiveness, energy efficiency, whether this helps to shed light on that where we sort of hit that limitation of the benefits.
Yes, absolutely. It definitely will. And the question of like cost appetite, like near-term cost appetite, is very intuitive in my mind. So I'm hoping that we'll be able to spend a lot of time on that slide, and hopefully we can dive into some of this then.
Okay, thank you.
Kara?
Hi, thanks, Nahi. Yeah, Kara Saylor from the Green Energy Institute at Lewis and Clark Law School. I have two questions, and forgive me, they're maybe kind of basic, but as I understand it from Elaine's questions earlier, right, continued operation of the thermal plants for wholesale sales. Will Oregon ratepayers benefit from the revenue generated from those sales?
Yes, that is correct.
Okay, and then separately, I understand that the company is viewing the delivery of renewable generation as not requiring the retirement of RECs. Similarly, will Oregon ratepayers benefit from the sale of the RECs that are not retired?
I might not be the best person to answer that. Seth?
Yeah, that's a great question. In this model, we don't incorporate any REC sales into the benefits that customers would face from generation. So no.
So Seth, follow up, is that because you don't anticipate them to be included, or just that wasn't something you thought about, or just
Definitely didn't think about it.
okay.
But now that we are, you know, it's not something really that we have the ability to project in terms of like the cost in the or the price in the market. And so we could, you know, we know with our project that Rob showed earlier, the projections of REC generation, and we know that they're going to be substantially over the RPS obligation. And so, and we know also the size of our REC bank. So we know how much we'll have available to sell. It would just be, you know, we could add the benefits of that sale if we had a price. And so because we don't have a good price forecast, we haven't included that, though very open to seeing, you know, what if you had feelings about what would be an appropriate price and quantity for us to sell of that REC bank, that could certainly be an analysis that we look into. Does that?
Yeah, I mean, I think, you know, well, you know GEI's perspective on this, but so the company is anticipating that ratepayers will get the benefit of the RECs that are generated associated with the renewable energy that they're paying for. It's just that it's not reflected in this model.
I'm very sure of the first statement. I haven't thought about, or sorry, the last part of that it's not reflected in this model.
Okay.
Less sure about the first part.
Okay.
Thanks. Eric?
Hi, thank you. A simple question. Is the ROSI or ART modeling open source? To what degree can OPUC or other stakeholders get a hold of this and twist the knobs and try other scenarios?
Great question. So ROSI, it's difficult because you need GAMS, which was state of the art in like 1970. I think GAMS is easy to get a hold of, but you need a solver. So that's tricky. ART is an Excel-based model that will be part of the docket, and so that could be easy to provide once we lock all data. I'm just thinking like, I'm trying to think what is the process for data sharing, but it'll be part of the LC80 docket. And so if you're an interreader there, we can share that with you and all our assumptions, and you'll have the ability to change any analysis that that would be of interest.
Thank you.
Sorry, go ahead.
Thank you.
Yeah.
All right. So moving forward, so we were talking about the why, and now let's talk about the how. So if we can move to the next slide, please. So the art, in a sense, has a relatively simplistic overarching goal here, right? So there are kind of two governing equations. They in a sense relatively simplistic, but except that everything is in sort of for sort of multiple years and multiple portfolios across multiple elements. So it gets complicated in scale, but fundamentally it's governed by these two equations. So starting on the right for both of these, on the top you see sort of the revenue requirement, and on the bottom you see the normalized revenue requirement, which is essentially just dividing the revenue requirement by the load. And the revenue requirement itself, I think, as people may have started piecing together, is a function of the fixed cost, the variable cost, the integration costs, other costs such as market purchases that PGE makes, and then the benefits that we talked about, which is the revenue generated from wholesale sales. And essentially, all of these are combined to get the annual revenue requirement. And so, the values that each of these provide in any given year is a function of several key inputs and several other pieces of modeling. But essentially, it comes down to these elements. So while they vary across portfolios, years, and other parameters, the fundamental equation is what's shown here. And so we can think of this as sort of a simplified way to think about the art. Right. With that, we can start moving into results. So we'll start with the preferred portfolio. So here you can see the results of the preferred portfolio. Just to orient you to the graph here, on the y-axis is your normalized revenue requirement. So from equation 2 in the previous slide, which is the dollars per megawatt hour. And on the x-axis is the years. And so we kind of see over time how actions in this IRP could affect cost. Now you will notice that there are several lines, and they all kind of start roughly in the same place, but diverge pretty significantly. And there are 25 lines. The line in red represents the following assumptions. It represents 50% PPA, 50% PGE ownership, and all tax credits that we have assumed in portfolio analysis. If we vary the tax credits, which there are provisions for which in the IRA and other policies that have come out, we see that varying the tax credits has an impact on the cost. So we varied the tax credits in sort of 5 separate scenarios. So we reduce the tax credit from what we have in portfolio analysis by 25% and by 50%, and then we increased it by 25% and 50%. And then you combine that with the 5 ownership structures that we talked about, which is the 0%, 25%, 50%, 75%, and 100% PPA assumption, and you get 25 combinations of potential cost futures that kind of exist based on procurement actions and contracts and the actual resources, right? So what we see generally, looking from left to right, is that over time costs are going up, and this is a function of the fact that we are adding resources to meet our decarbonization goals and adding resources to meet our capacity and energy needs as well. So all these 3 combined, the net impact is that on average, costs tend to go up. If we can, through our procurement process, figure out, a way to maximize these tax credits, you start seeing numbers that are lower than sort of the red line, which if you want to think about it, it's 100% tax credit, and then everything up below that is over 100%, 125 and 150. So essentially figuring out how tax credits feature into our procurement process will be a very effective strategy in reducing rates as shown here. And in cases where we aren't able to leverage the same kind of tax credits, we will see costs kind of go up. In years where you see large dips in prices, like you can see in 2026, you will notice that that happens only for scenarios where there is a significant PGE ownership, and there is usually a battery resource procured in that year. So what is happening is that the ITC impact of the battery is sort of realized in year one, and that benefit is then, because it's owned by PGE, that benefit is then transitioned through PGE into rates, or essentially into prices, not necessarily into rates. Apologies, that into the prices that we see, and those prices would go down as a function of the ITC credits that are being realized in year one. Whereas a PPA would essentially see that credit get levelized over the life of the equipment. And so in the short term, you see some of these PPAs kind of having a larger impact on prices because of how the tax credits and their implications on near-term costs are accounted for. And so that tells you the dynamic in terms of ownership and the dynamic in terms of tax credits. And so again, the results post 2030 and especially post 2030 are very sensitive to the generic resources. And so that has to be in mind as we think about it. And again, applying percentages to these numbers and sort of thinking that these are actual prices the customers will pay is not the takeaway here. The takeaway is largely that costs are increasing. Tax credits are a great way to offset them, and we have a few other elements. So diving a little deeper into the specifics of the graph, from 2024 to 2025, we see the a cost increase. The cost increase is largely associated with those 2021 RFP resources, which we have assumed to be 100% PPA. Right, so we talked about that, the impact of those resources which are coming online in 2025, or we expect them to come online in 2025, are seen in 2025. So that would be their first year in service. The 2026 reduction is because you can see in the preferred portfolio, we are adding about 230 megawatts, a little over 230 megawatts of storage, and the ITC benefit of that is seen in that red line dipping a little lower, and then consistent with the remaining build out, you can see patterns sort of emerge. And so you will see that there is if you overlay this with the resource build out, you should be able to see like resource actions that are impacting the costs in the relevant years. All right. With that, we can move to the next set of results. So the next two slides are focused on the decarbonization glide paths, and then we focus on energy efficiency. So to start with the decarbonization glide paths, now just again to orient everyone to these graphs, on the y-axis is the difference in dollars per megawatt hour of two portfolios, right? So there is the reference portfolio. In this case, it's the linear glide path, and a comparator portfolio, and the portfolio we are comparing, which is in this case on the top right here is the portfolio where we achieve 100%, we're decarbonized 100% by 2035, right? And so what we see is that when we try to decarbonize 100% by 2035, as Rob showed earlier, the NPVRR is higher, and this shows when the costs are kind of hitting the books to create that higher NPVRR, right? So we would largely see those costs accumulate in the 2030s, from 2030 to 2039, and we see those costs increase pretty significantly. And so if you think back to sort of one slide ago, where the base cost for 2024 is around $80, and like it's already increasing from there, in 2035, it would increase from what the linear glide path has increased. So let's say the linear glide path were, just as an example, at 100, this would be $125 in 2035, right? And so it's talking about the increase beyond the linear amount, not from 2024, right? And so we look at these and we see that the costs are increasing over time, and we see that those costs are over the linear amount, which is also increasing over time. And so we need to think about that. A quick mention, the error bars that you are seeing in each of the bars here represent the standard deviation in the difference between the different ownership and tax incentive structures, right? So we had the 25 combinations of tax and ownership structures. And so the standard deviation of those is represented by the error bars. And hopefully that gives you a sense that like signing different contracts and different contract structures with different tax incentives could lead to that amount of variation. And that is the standard deviation, not the entire range. All right. Looking at the graph below here, we see that when we shift our HB 2021 targets 2 years ahead of time, cost increases start as soon as 2028 and sort of stay consistently up above the linear decline through 2039. And some of those benefits of like doing these things a little earlier are experienced towards the end of the planning horizon or even beyond the planning horizon that we have evaluated here. But there is a lot of uncertainty there. So, the little bit of a grain of salt as you think about, are those benefits kind of worth it? And as we know on an NPV-RR basis, over the planning horizon, they are not. So these two graphs effectively show a different dimension than the NPV-RR and the risk metrics we've seen earlier. But they drive to somewhat the same conclusion, which is adding resources to reduce emissions, increase costs. And that is really pertinent, right? Like and you see how that happens when you try to ramp up to address emissions by 2035, costs increase in that range. When you try to accelerate everything by 2 years, costs are increasing across the board. And so while it gives you a different dimension, it does not necessarily change the takeaway, which is going faster than HB 2021 mandates. This will result in a more expensive system. And so the question about how do we balance these things? And the best way we think to balance it is to meet HB 2021 on target, as we think is sort of optimal here. And so on the next slide here, if we could move to that, we are focusing on the 3 glide paths the 3 glide paths through 2030. Right. And so relative to the linear glide path, we want to compare the front-loaded and the back-loaded glide path. Right. And so the front-loaded glide path, you can see that the cost increases are seen as soon as 2026 and go up all the way to 2030. And you can see there is definitely a large range in sort of costs depending on the different tax incentives and ownership structures there. But essentially, it's an intuitive result in that we are adding resources earlier, and we know that resources costs decline over time. And so there are kind of 2 impacts that are happening. You add more resources earlier, meaning the front-loaded portfolio is more expensive. And because resources added later are not as expensive, the impact is sort of magnified in other years as well, right? And so both of these are kind of seen here. And then there is this little bit of increase in cost in 2037 to 2039. And that is associated with the PTCs expiring for the resources that are added from 2027, right? From 2026 and 2027. And so essentially what's happening is that because those PTCs expire earlier in the front-loaded portfolio, the front-loaded portfolio is seemingly a little more expensive than the linear decline, even in those years. However, in the linear decline, the PTCs expire a little later, And so by 2040, the same amount of PTCs have expired in both. And so the difference goes to zero. And so that little bit of interaction in the post 2030 timeframe is largely associated with PTCs expiring. The backloaded one, as as Rob mentioned, has a lower NPV-RR, but has several elements of risks, right? Like we talked about the procurement risk, the integration risk, the regulatory risk, and all of those things. But on a cost basis, it's lower cost, and you can see how those costs kind of pan out. They largely manifest before 2030 and then 2030, because there is a significant resource addition then. Those costs are kind of evident, and then 2039 refers to some of the PTC expirations that we just talked about. And so happy to take question about the GHG portfolios. I think Elizabeth.
Thank you. On this graph we're looking at right now on the front loaded and back loaded, we talked earlier about how the assumptions could be changed for how much competition there might be and how there was different opinions at PGE. It'd be very nice to see this graph also with the assumptions changed.
Yeah, absolutely. I think when we are thinking about this analysis and how we set it up, we would like to do it sort of end to end and make sure we are reflecting all the changes across all the models to see how it's impacting. So definitely something we'll probably be doing as we think about that analysis.
Thank you.
All right, I think we can move to the next slide, which is focused on energy efficiency. All right. So I'm going to take a couple of minutes to set up this slide because there's a little bit going on here, but I think once it's set up, it should be relatively intuitive. So I'm starting on the far right here. So the graphs in red are the NPV-RR metrics that were shared earlier. And so you can see that Rob shared, a few portfolios where energy efficiency lowered the cost compared to I shouldn't say energy efficiency, I should say additional energy efficiency. So apologies. Additional energy efficiency can reduce the cost compared to no additional energy efficiency. And that is seen in sort of the first two rows, right? If you want to think about it that way. So the top graph and the middle graph show that when you add energy efficiency, the NPV-RR metric reduces. And then the third graph at the bottom shows that when you add additional energy efficiency, the NPV-RR metric increases. And so to visualize the impact of that, we have the graphs on their immediate left. So starting from the very top, 25 megawatt average of additional energy efficiency creates the lowest amount of near-term rate impact. And so you can see that increase in rate impact from 2026 through 2030. And then once the additional energy efficiency is exhausted in 2030, we see the benefits of energy efficiency pretty clearly, right? And so you see that the NPV-RR metric shows that the bars going down outweigh the bars going up. But the question is of affordability in the near term, right? And so, and the reason affordability in the near term is kind of front and center is because that's what we've heard through both our discussions here and in other CEP discussions. And so we see that increase in the first few years, and the increase in the first few years is a function of how we treat energy efficiency in the current policy environment, right? So in essence, as a function of the policy we have, we see a higher price impact because of energy efficiency in the short term. And even though there are significant benefits in the long term, the question about short-term affordability becomes front and center. excuse me. This impact is sort of exacerbated as we add more energy efficiency, right? And so the second graph here effectively doubles the amount of energy efficiency, additional energy efficiency that we add between 2026 and 2030. And you can see that the price impact is pretty significant. And in 2030, if you want to think about it relative to what we saw in the preferred portfolio, that's it gets to more than 5%, just the impact of energy efficiency in that portfolio, right? And so you see that these impacts are pretty significant in the near term, even though, again, the long-term benefits outweigh the near-term costs. And so the question becomes really about cost appetite. Do we, when we sort of collectively decide, like, is it kind of worth the near-term cost pressure to get that long-term benefit? And the way we've been thinking about it, we don't think it is worth it. And I think that's kind of how we've been talking about it. But happy to take questions. I know there were like 3-4 questions that were all alluding to this slide, and I hope some of them have helped make the questions more specific, so we can maybe dive into it. Elizabeth?
Thank you. The conclusion that you mentioned is being hidden by the way the graph is made. You should be using the same y-axis in each graph so that the result is really obvious, instead of the graph actually being the opposite of the conclusion because the y-axis is changed in each case.
Yeah, I think you're right. I think if you had the same y-axis, the effect would be more pronounced. Yeah. Or more, I guess, interpretable. Yep.
Elaine?
Thanks. You talked about this notion of an appetite for near-term cost increases, and I'm curious if engaged sort of community-based organizations or other representatives of your customers to understand the or to sort of inform that thought process with regard to energy efficiency.
Happy to take this one too. No, the timing of this has prevented that. I think a more robust community engagement would have been better, but really the socialization of these results, this is the first time we're showing these price impacts because honestly, we didn't have them a week ago. And so we haven't engaged in communication of that trade-off. The general story we've been telling since I don't know when we started, maybe December's roundtable or January's roundtable, but no, we haven't done much engagement other than this roundtable series to make this judgment call.
Nikki, do you have more content to present on this slide? I think this might be your last one.
I believe that's right.
Okay. I'll pause just for a second, just in case anyone has another question, but oh, Kim.
Sorry, I hate to be here at lunch. And can you just tell me, Nikki, whether this, with the ART assumptions, we've got this as $ per megawatt hours. Maybe I just didn't follow, but when we talk about impact to customers, and we're talking about like if it's ultimately translated into $ per
kilowatt, does this also account for the reduction in kilowatts used because of the energy efficiency measures? Okay, thank you. Just
Yeah.
make sure. Just gonna check.
Yeah, so the current policy has kind of two implications. The first is that energy efficiency is funded 100% in sort of that year or the year like before it, right? Like, so if the Energy Trust wanted to do X amount of energy efficiency, it's not financed over 20 years. It's that cost is borne by customer in that year or in the next year. And because it's not financed over a long time, we see some of these impacts happen. And the other piece is that the reduced sales from energy efficiency creates upward pressure on prices, which also add to the fact that it's not being financed. So it is actually a double whammy, if you want to think about it that way, where those two combined impacts lead to a significantly higher price impact pressure compared to other resources, which are both financed and they don't reduce sales, so they don't have that upward rate pressure. And so it really is, in a lot of ways, a policy decision about how we treat these resources more fairly in a way to compare them with other options.
Okay, thanks.
And to add on to that answer, we are in the IRP. As we were kind of discussing earlier, we're trying to highlight the differences here in planning processes, and so hopefully we as an industry can better align what we're seeing out of portfolio analysis and then going into the evaluation of these energy efficiency resources. We said we've been struggling with the term non-cost effective because that's how they came out of analysis based on 2019 IRP inputs. But when you look with everything we know and are studying now, they do look much more attractive as resources, especially in a long-term front. And so there will be language included in this coming IRP as to the reasons why, both the calculation of avoided capacity and avoided energy. And so hopefully we can, again, as an industry, because this ranges a number of dockets and processes that we follow. Hopefully we can all get aligned to have a more reflective calculation of these resources. Hopefully that made sense.
Thanks, Seth.
So Shadia, would you stop sharing your screen and pull up that table that we presented on that had kind of those years off? We fixed this table and we just want to present it. It's a really important piece that we want to make sure the correct information is presented. So we're going to present that now and just recalibrate to make sure everyone's seeing the correct version. And then we're actually going to adjust our break forward. So we take a 30-minute break starting as soon as we're done sharing this, just to make the rest of the topic flow well. So yeah, Seth, did you want to present this, or Nahid? I wasn't sure what we had to say here. Okay.
I'm happy to. This is just the corrected version. So we made a change in some of those columns and it pushed resources forward inadvertently. So this is the correct version. The graph that was on the preceding slide was correct, but this table was not. They're supposed to show the same resources they didn't before. Now they do. The slides that we send out shortly after this presentation, that will reflect the corrected version.
Correct. Eric? Eric, did you have a question?
Got to unmute here.
Okay.
A couple verification questions. I assume this does not include any value for resilience, such as mandates or incentives to do anything regarding local build outs or earthquake preparedness or wildfire hardening. Is that correct?
Yeah, so the portfolio analysis, the preferred portfolio is a result of all the portfolio analysis. And in that portfolio analysis, there were no constraints such that you were describing. That said, we in the filing that we have in a couple of weeks, we do have an entire chapter devoted towards our approach to resiliency and what we're doing as a company towards that topic.
Oh, that's good. One other verification, you're not including any kind of bidirectional EV charging as a either demand response or storage, distributed storage.
So that's a great question. We are including all of the demand response projected from the DSP Part 2. The question of bidirectional EV storage is something I'll have to follow up. Unless anyone on this call can answer definitively, we can just follow up with you as to whether that's included, and if so, how much.
Okay, thanks.
Okay, thank you. So we'll take a 30-minute break now. That means we'll come back at 12:45 and get started with the latter part of this topic, and then finish our other two topics that remain. So again, you can leave the meeting and join back with the same link, or just mute yourself, and we'll see you in 30 minutes. Okay, welcome back. Hope everyone's ready for the last part of our meeting. So Shadia, if you could go to one more slide, that's great. And we'll get started here, pick up where we left off. So for the draft action plan part 2 today, Tomas is actually out of the office, and so Seth is going to be taking this topic. So Seth, when you're ready, you can go ahead.
Yes, thank you, Jesse. So if you're following along with the slides, we skipped ahead a little bit here. There are additional portfolios in the portfolio analysis section after, if you look at slide deck, it's after the art presentation. So starting on slide 72 and going up to this, which is slide 93. So in that section, there are additional portfolios, including the targeted policy portfolios, the optimization portfolios, and the emerging technology portfolios. The reason why we're skipping ahead is because just in the interest of time, we want to make sure we have sufficient time for both the action plan and the RFP section. The earlier portfolio analyses sections are largely a repeat from what we did in January, similar to before, but the conclusions are even less changed from January. So if there's interest, happy to go over any of them. Also being skipped over is the robustness checks that we have run on the preferred portfolio. Again, this is in the interest of time. If there is specific interest on any of those topics, or just general interest, happy to go over that. But we're going to start this presentation on the action plan. Try to cover that for now, and then move to the RFP section. And if there's time or interest, we'll take a look at the earlier portfolio analysis sections. So then turning to the draft action plan, it's something we've talked about before. Shadi, if you please move to the next slide. So we talked about it in January. There were 5 main components of the action plan. building on the findings that we found from the preferred portfolio. And today, we're not presenting anything really all that different, except for some slight edits in the energy need, capacity need, and the transmission plan. So we can just get right into it. The next slide says these 5 components of the action plan. So starting with customer actions, the CBREs, the energy action, your capacity action, and the transmission action. Starting with this first one, there are some different numbers that you see here, and this was also reflected in the preferred portfolio when we showed the tables and the in the graph. So the action itself is to acquire all cost-effective energy efficiency and incorporate the customer additions of demand response. Now, the demand response values are the same as before, though in the tables we showed before, there's some additional information filled out for years 2024 and 2025. For the energy efficiency, we also added those 2024 and 2025 values. And so the cumulative additions now appear larger, but we're taking from the same data set, if that makes sense. So basically we're saying acquire everything that's in the cost-effective forecast coming out of the ETO, and that's going straight into the action plan. The number is about 60 average megawatts higher because now you're incorporating those 2024 and 2025 additions. I hope that makes sense. This isn't a change in terms of the non-cost effective resources. This is just sticking to the cost effective resources, but the numbers are higher, reflecting that we're not talking about 2026 to 2028. We're now talking about 2024 to 2028. So hopefully that makes sense, that the numbers have changed, but it reflects the same data set. Okay, on the next slide, we talk about the CBRE action. So this is targeting 66 megawatts in 2023, building to a target of 155 megawatts by 2030. These estimates, both of the costs and benefits, come from our DSP team, and we are incorporating basically the full potential based off of IRP analysis that showed that CBREs are, given everything we know about transmission constraints and the relative economics of all resources available to us, I think that CBREs are a cost-effective resource, and accordingly, we think they should be incorporated. Now, these are proxy resources. Of course, there's going to be a difference as to what shows up in the RFP, but our IRP modeling, even based on the proxy resources, saying basically do everything. And so we think it's appropriate to move forward to try and acquire the total technical potential that we think is out there. The next slide outlines the energy action. So you do see a slightly higher average megawatt 2030 need, and dividing by 5, you see about 180 average megawatts every year from now till then. This assumes the incorporation of the entirety of the energy efficiency and demand response forecast that we discussed earlier. So this is on top of that. Should any of that not materialize, these targets would be higher. CBRE additions could reduce this need by about 30 average megawatts. And so that could slightly reduce this target, but this 2030 need divided by 5 is massive. So 181 average megawatts, that's a very large number for every year going towards 2030, and it highlights the challenge ahead of us. But by and large, this stays the same as what was previously communicated in January. The same structure of the action item and the same type of calculation, though the numbers have been updated. Capacity action, slightly updated numbers as well. So instead of looking at the 2030 value and basically divided by the years available to add those, we are just looking at the 2026 need estimated to be present in 2026. As we discussed before with JP and Kim, we think that it's appropriate to pursue what we can in the bilateral market, as well as the CBRE additions, and incorporate whatever change comes from them into this RFP. So targeting this 2026 capacity need, but incorporating anything we do before then. So an example from the 2019 IRP was that I think it was a 2025 capacity need of about 588 megawatts was identified. I think that's the number. And then the re-signing of the Pelton Round Butte facility was enacted, and that reduced the capacity need that went into the 2021 all source RFP. So similarly, we think any bilateral contracts that we're able to secure should go, should be incorporated into those targets, and that RFP designed to fill the capacity need in 2026 would be the most up-to-date target that we have. And then this last component is to do two parts of the transmission expansion. So first is pursue all options available to alleviate the congestion on the SOA flow gate. So basically that would enable whatever could be done to alleviate our constraints that we have getting resources off system across BPA's system. We think we should be pursuing. And then one of those specific projects is the Bethel to Round Butte line, upgrading that from 230 to 500 kV. We think this is a option that provides a good amount of near-term relief to these transmission constraints for future PG load service. And so I think this is an option that is warranted to be in the action plan, and something that we're planning on pursuing. Yeah, I see we have a question.
Yeah, Seth, this is Bill Pasco again. I'm thinking your transmission slide from the action plan is missing a third step. We talked in the preferred portfolio about exploring opportunities to participate in transmission to other areas, and those things have long lead times, and I would think you'd want to be working on that right away, even though it's not something that would occur in the next few years.
That's a great point. I appreciate the comment. We've talked a lot about this internally, and basically where we've landed on this specific point is that it's not something that we're asking for the commission. It's something that we're doing. And so things that go in the action plan are things that we are proposing to do. And so that study of existing regional expansion is something that we're actively doing right now. We're learning how to model, as you can tell from the transmission components in the IRP, we're learning how to do that, but it's something that we understand that is and we're actively pursuing that.
Yeah. So Seth, in your Oregon process, I guess you asked the commission to acknowledge certain things, and that's kind of a nod to go ahead and do them. And at one time, I remember there was been some discussion about asking the commission to acknowledge that more interstate transmission could be a good thing. So if you don't put it in the action plan, does it not get acknowledged?
I think the answer to your question is yes. If it's not directly in the action plan, it wouldn't be acknowledged. That said, if you read the order from the last IRP, the commission weighed in on a number of issues that went beyond the specific action plan. And so I think it's a relevant expectation from the coming docket that the commission is there's lengthy conversation about this topic among parties as well as the commission. So I would be shocked if in 6 months this isn't widely discussed among parties.
Okay. Thank you.
Yeah, those are great questions, and we've talked a lot about them as to what's appropriate to be in the action plan versus what's what we're already doing versus what's going to happen in the docket. So yeah, definitely appreciate the inquiry.
Seth, this is Randy Hardy.
Yeah, go ahead.
Question is, are your transmission options generally just PGE options as opposed to things Bonneville needs to do? I mean, you've got some of both to cure or to acquire the resources, but I wanted to make sure I understood the distinction here.
Yeah, great question. In the action plan, these are things that PGE is proposing that we do. There are many things that we would like others to do, but those are not included in the action plan.
Okay, second question. There are a number of I'll call them Portland area upgrades that are necessary that involve both Bonneville and PGE action. Ross Rivergate, some others that relate to south of Alston and whatnot. Are those things aren't in here? Do you consider those more local things that have to be done as opposed to something that's more interregional that's appropriate for the IRP?
Yeah, that's a good question. So I'm going to ask Sean Foster to weigh in on those specific projects. But there is, I would just say in general, there are many things that we are planning to do for local reliability and system stability that are not included in this action plan.
Yeah, understood.
Yeah. Hey, Randy, this is Sean. And,
yeah, Sean.
And yeah, to second what Seth is saying is what's going in the action plan are sort of the unilateral things that PG can do, essentially unto itself. The Ross Rivergate component of it is the only component of that PG would have would be rebuilding the last, structure or two, and then, dealing with breaker issues inside of Rivergate proper. And so that's, really a Bonneville project. And the absence of specifically calling out things in here that are Bonneville actions, or it's primarily because, what's in the sphere of PG's control are the things that we can do unto ourselves, right? And so that's really, what this action plan is about, or what are the things that PG can do. Now, if there was a larger project that, let's say, I'm just throwing out a hypothetical that Bonneville proposed that, PG was jointly going to work on them with, that, rose to the level of, something more than what Rivergate is, which is, would just be, a few components in a single substation. Potentially it could find its way into the IRP, right? But, at the end of the day, those projects out of the Bonneville TSEP are really Bonneville projects. And then, to the last point, those other issues, Bonneville commonly refers to them as like subgrid issues that really relate to more local load service constructs. Those are happening, right? That's transmission work that PG's been doing for forever. Just that relate to, more local load service, subgrid type of efforts.
Yeah, Kara?
Kara, if you're talking, you're still on mute. I didn't know if you.
Sorry, my computer
There
was
you go.
not accepting me unmuting it. Here I
No
am.
problem.
So I just wanted to note, following up on something Bill Pasco mentioned, what to include, what not to include in the action plan. At stakeholder suggestion to Northwest Natural, they included something in their action plan and just provided a note that that was the issue was the specific action item was part of their compliance strategy, but they were not asking for acknowledgement from the commission of the item since they were already pursuing the action. And I'll just say that might be a good solution because it provides a lot of clarity to stakeholders about what it is you are doing, and just having it front and center in the action plan is just, I think, really helpful for stakeholders to see what the plan is and what you are doing. You can just note you're not seeking acknowledgement on that item.
That is extremely helpful. Thank you. Yeah, we'll take a look at that. Other questions on transmission or just the whole of the action plan? Yeah, JP.
Hey, thanks, Seth. It just to follow up on something Randy said, and just wondering, would it be possible in the IRP, and maybe not as part of the action plan, to lay out what are the key requests that you're making of BPA as part of an action plan? Like, here are the top 3 things or top 2 things we're working with BPA to pursue that would help us meet our goals. So not necessarily an action per se, like you guys are delivering, but rather what you're doing to engage with BPA, and obviously not you, but PGE broadly, with BPA in the near term. Like, we're going after these 3 things or these 2 things as part of our action plan. Just wonder if that might be a really part of the action plan, address what I think Randy's good point.
Yeah, I think that's a great suggestion. There's, I guess, 2 parts to it. One I'm sure about, one I'm not. So I'm sure that it would be useful for us to communicate to all of you and all interested parties what we're doing on the BPA front. Where it goes in the IRP, I'm not sure. But yeah, I'll definitely take that back and try to answer both questions.
Yeah, and just by way of background, for the stakeholder community, like staff and everyone else on the call, to have an understanding of what you guys have identified as a really key near-term thing BPA could do, allows us to, even to some degree, to engage in different forums around those issues, right? So
yeah, absolutely.
Thanks.
Yeah, Seth, this is Randy again. I've talked a lot with Sean and with Larry Beckett and whatnot, and you guys are doing a hell of a lot of work with Bonneville on all kinds of things. And just to get some credit, if nothing else, but it gives you that would, JP's suggestion or some version of that would I think give people a lot more idea of the tremendous amount of effort that's going in, not just to meet your 2030 decarb goals, but to serve all the new load in Hillsborough.
Yeah, absolutely agree. I think to describe half of Sean Foster's day would be an impressive thing. So yes, I agree.
Well, Seth, if you're ready, I can move on to the next and last topic.
Yeah.
Okay. Let's go forward 2 slides, I believe, to the topic. Yeah, there we go. Okay. So we have Shiraz Bengali with us today to present on the 2023 All Source Request for Proposals. Shiraz, you can go ahead and start when you're ready. Just let us know when to advance the slides and we'll move them forward. And then we can take comments while you're presenting information. So if you see a hand up, go ahead and take it. And if I see one, I might interrupt you and have you take that.
Thanks, Jesse.
Yeah.
Yeah, good afternoon, everyone. My name is Shiraz Bengali. I'm a senior originator on the structuring origination team, and my team's focus is on long-term energy procurement. So if you don't mind moving to the next slide, please. So today I'm just going to share some details about PG's initiation of the 2023 all-source RFP. As you've seen in this 2023 IRP roundtables, PG expects there to be both non-emitting capacity and energy needs within the action plan window. So to meet those stated needs timely, PG filed to initiate the 2023 all-source RFP in January with a request to streamline the process while maintaining a robust regulatory process. And just to note, the procurement volume sought in the 2023 RFP will align with the 2023 IRP action plan once an acknowledgement decision is made by the Commission. So if you don't mind moving to the next slide. And so specifically, the RFP will be supporting the energy and capacity actions that Seth just outlined in the previous section. So this RFP, PG will look to find products that can meet the 2026 capacity need and also continue to make progress to HB 2021 targets. And all actions that are taken up until the IRP acknowledgement, whether in bilateral negotiations or CBRE acquisitions, for example, will be reflected in the targeted procurement volume. So there will be alignment in terms of what procurement volume is made in this RFP with the IRP action plan. Next slide, please. And so when we're initiating this RFP, we were trying to make sure that we stay aligned with the IRP action plan, and we arrived at the timing to initiate now by working backwards in this timeline that you see here, and starting on the right with the significant 2026 capacity need. Project takes about 18 months for construction, then there's 3 to 6 months needed for commercial negotiations, and then another 4 to 6 months for RFP evaluation phase, and then 6 months for the RFP design kind of regulatory approval process. And so that really gets us to starting now in order to meet that 2026 deadline. Next slide, please. Here's just some details about what was requested in the January filing. So just before I get into that, there's 3 main procedural phases in the RFP approval process. So it's the IE, RFP, the scoring and modeling methodology, and the draft RFP. So our first request is for an extension of Bates White, who is the IE in the last RFP process, and we wish to extend him into the 2023 RFP. That would remove the IE RFP phase from the schedule. And just as a note, the last IE RFP was just conducted less than 2 years ago for the previous RFP. Our second request in the filing is to waive the procedural requirement to seek approval of the scoring and modeling methodology before the draft RFP. So instead, we just collapse that review into the draft RFP phase, where there'd still be robust opportunities to review the RFP structure. And we'd intend to use the 2021 RFP scoring and methodology as a base and then iterate off of that. And we're not asking for any sort of pre-approval of any sort of scoring requirement. It's just, again, just kind of combining those phases into one. And so these 2 requests would help streamline the procedural process, remove 4 to 6 months from the schedule, and still retain many opportunities for stakeholder review. This would enable the RFP to stay in line with the stated IRP needs and timely provide resources by 2026. Next slide, please. So these are just kind of the near-term next steps. We anticipate the Commission making a determination on the waiver request and establishing a procedural schedule. The IRP CEP will be filed this month, and then our goal is to have the draft RFP issued in April and then get it approved and then to market in Q3 of 2023. And that's it for me. So thank you. And now I'll open it up to any questions that folks might have.
Bill, go ahead.
All righty. Shiraz, one of the things that's been a sticking point in past IRPs has been the availability of transmission rights for resources to get to Portland. And in the past, my recollection, which is not always perfectly clear, is that PGE had kind of a portfolio of transmission rights on Bonneville, but those were not available for participants in the RFP. You were supposed to bring your own transmission. Is it possible that that will change in this next RFP?
So I'll just first by stating what the requirements were in the last RFP. So for renewable resources, we required 80% or more long-term firm transmission. And then for dispatchable projects, we required 100% long-term firm transmission. And I understand the question in basically making available PG rights to transmission. And I guess maybe Sean is on, or some other transmission expert on our side can answer more of the details specifically, but I think we've stated before within dockets that there are no excess transmission rights really to be made available. And so that's kind of what we continue to see, and likely we would see again in this RFP process as well. So I'll leave it for anyone else on the team has some more to say on that front.
Yeah, Shiraz, let me give an example. Puget, in their resource planning processes for a lot of years, had roughly 1,500 megawatts of transmission rights between their service territory and Mid-Columbia. And they basically held those out because they were going to use those for market purchases. So there was a piece of their portfolio that they were depending on the market for, and they needed transmission to get it. In their last cycle, they've changed the plan because they're concerned about relying too much on short-term market purchases. And so now they're using some of those 1,500 megawatts of transmission rights to Mid-C to bring in more renewables so that they can meet their decarbonization goals. And I don't know if there's an analogous situation at Portland General, if there might be some transmission rights to Mid-C or other places that have historically been used for opportunity purchases or for even short-term capacity purchases that could be repurposed to bring in renewables, or could be shared with renewables without creating a reliability impact.
Yeah, thanks for that example. And I think, yes, we have looked at that in the past, and we will continue to look at whether there are rights that can be made available. And I think that will be something that we'll likely discuss in the subsequent review of the RFP design. So that will definitely be a topic for conversation there. But thanks for the question, though.
Okay.
Other questions or comments? Okay. Well, thank you, Shiraz, for joining us today. We can move to, yeah, thanks. We can move on to our next step slide and closing. Okay. So just to wrap up the meeting today, a recording from today's webinar will be available in 1 week from today, possibly sooner, but definitely 1 week from today. And we should be able to get the slides up onto our website tomorrow. So, and that will include the updates to that table that we showed you the corrected version of. Then our next roundtable is March 30th. That's our final roundtable of this current IRP cycle. And our filing deadline is March 31st. So those are our key dates to pay attention to. And then if you go to the next slide, you can just see the email address where you can reach us if you have follow-up questions. I did note down a few items to follow up on with individual people, so we'll be reaching out to you in the next couple weeks to follow up with specific questions. And then we'll address any general follow-up topics in the March 30th roundtable. Other than that, I just want to thank everyone for being here with us today, and I'm gonna go ahead and close out the meeting.